2 minutes.
Okay. We'll wait for 2 minutes.
Will start.
Sibi, you are muted.
Raji, you can start now.
Yeah. Good afternoon and welcome to the second day of JNCASR-FCBS workshop for the college students and teachers. And as in the previous day, I request all the participants to kindly mute your microphone. And if you have any questions, please post in the chat box. The chairman will pick up your questions and will be addressed by the speaker. Okay. And I now invite Dr. Joshi Joseph to chair today's session. Dr. Joshi.
Thank you, Raji, and good evening to all participants. Today we have the second session of this year's workshop, and we have three talks in this section. And first talk is by Professor R.B. Sunoj from Department of Chemistry, Indian Institute of Technology, Mumbai. And I think for the teachers in Kerala colleges, Sunoj doesn't need any introduction. And for the students who are new to the system, Sunoj is a wonderful teacher, and you will experience that. And he has done his PhD from Indian Institute of Bangalore and then postdoc from Ohio State University, Columbus. And is a professor at Department of Chemistry at IIT Mumbai, and he is actually an organic chemist using computational methods for doing the chemistry, and he will talk more about that in his talk. And he is awarded with last year he got the Shanti Swarup Bhatnagar Award, and he has several other awards in his bag. So I don't want to waste any of his time. So let us invite Professor R.B. Sunoj to deliver the lecture. Thank you.
Thank you, Dr. Joshi, for the kind words of introduction. And also thank the organizers, Bala and many others who have been pushing this FCBS. I have always enjoyed interacting with students and other participants all these years. I consider it as an opportunity to give back to the state and the place where I grew up. And I have been one of the beneficiaries of FCBS earliest versions. So it's a good feel to give back in whatever capacity which I may be able to. So with that said, I have decided to do a couple of things not so conventional. One is to use a conventional mode of teaching. Not really a seminar. It's a conventional mode of teaching using Blackboard. It's a whiteboard, of course. You know, in a time of pandemic, everything is upside down. So I call it as a Blackboard, and I will use to draw using black pen. Hope it is visible to you. So.
Sunoj, you are not audible, and somebody else's voice we are hearing.
Okay. Is there an option to mute all participants?
All are muted. I'm trying to see who was that.
Having
Sunoj, you are muted.
Yeah. In between somebody. Yeah.
Audible?
Yeah. Audible. Please.
Okay. Yeah. So I will talk about problem-solving approaches by taking a few representative examples. The examples will come after some time. So before I go.
Continue.
Yeah, before I go further, let me first describe what is the global agenda today. It is to talk about structure, property, and reaction, and how these are interconnected. This is going to be the key objective. Structure, property, how structure or geometry would affect property, and property, the best of all property a chemist can imagine is reaction or reactivity. Professor Maitra's talk was illuminating yesterday. He talked about various methods to identify reaction mechanism, particularly the kinetic aspects of it, rate of reaction, how do you understand chemical kinetics of organic reactions. That was quite an interesting lecture which laid the foundation. I was acknowledging with Professor Maitra that you have laid the foundation, so I don't have to talk much about the kinetic aspects of it. Now, I'm going to connect these important ingredients an organic chemist would deal with, structure, property, in multiple ways. And to begin with, the property and structure are interrelated by what we call as molecular orbitals, which would be one of the important points that I would discuss, molecular orbital and its ramification or its connection to organic reactions. Now, let me elaborate on the structure aspect of it. If I want to elaborate on the structure, as organic chemists, one would first talk about the tetrahedral structure. This is extremely important. And one would assume that I know tetrahedral structure. Many people thought, yes, they know tetrahedral structure. But the implications of tetrahedral structure and the clear understanding of what is actually a tetrahedral structure and how you can connect with a given drawing. For example, I'm holding a tetrahedral molecule. Of course, this has two tetrahedral structures. If I may show you this molecule, this is a tetrahedral structure with 4 substituents attached to the central carbon. Now, a good appreciation of tetrahedral structure is the key to understanding higher analogs. For example, if I talk about ethane, methane to ethane, all that you are faced with is your appreciation about tetrahedral carbon. And I can progressively construct all carbon, saturated carbon system, go all the way to cyclohexane, substituted cyclohexane. That is going to be the focus of some of the problem sets that I would talk about. One could even go to higher analogs of something called a bicyclic system. I'm sorry about the background, maybe this would help. The bicyclic system such as, it's not an ad for Wacom products, but I use this Wacom tablet to teach online occasionally. So this is a bicyclic system, what we call as decalin. This is also important for today's discussion. So with that said, let us have a close look at tetrahedral structure, because I'm going to tease you with this very same concept as we proceed. So if I look at this tetrahedral structure, one of the things that everyone should understand to begin with is different ways of representing tetrahedral carbon. And we don't have the luxury of having this kind of models in a classroom setup. Neither we have that luxury in an exam setup, because that's what students end of the day care, right? They care about the grades and exams. So if in an exam, we are always left with this representations, what we call as different projection formula. And projection formula is extremely valuable for us to be able to convey this 3-dimensional tetrahedral entity in a piece of paper with the help of pen or pencil. So let me just talk about tetrahedral. Appears to be trivial, but I will bring home certain points today. So if I were to hold this molecule in this manner, and I can see that there are two substituents not on the plane created by, let's say, this atom, this carbon here, and this carbon. They form the plane of the board. And then you have this one substituent facing towards you. Let's call it substituent A, and another substituent which is away from or below the plane of the board that I call as substituent B. So this is a decent depiction of tetrahedral carbon. And of course, you can look at this in very, many different ways. If you were to look at from this direction, you will see that A is on my left side, B is on my right side, and I can use this dot here, and I call this as a flying wedge representation, and this I call as a Fisher projection formula. These are all useful textbook concepts and which appears in multiple ways in different problems as one would try to solve organic problem sets. But now if I try to connect this and make a two carbon system, and that is where the game begins in extending the concept of tetrahedral carbon. So I'm holding this molecule in its eclipse geometry. Let us assume that all are hydrogen, including the one which is shown in green and red color. So this is an eclipse geometry, and we can represent this eclipse geometry using another projection formula, very, very important, very valuable, what we call as a Newman projection formula. And this is the equivalent representation for this eclipse geometry. Now, if I rotate this molecule along the permissible carbon-carbon single bond, I can go to a geometry or a conformer known as staggered conformer. And here comes one of the associated property. When we talk about structure, we always implicitly talk about stability. And with respect to this eclipse geometry, and I have this staggered geometry, which is lower in energy, I say that the staggered is lower with respect to eclipse geometry. If we are dealing with ethane, for example, this height, the energy difference between these 2 points on the potential energy surface will be about 3 kilocalories per mole. What am I talking about? I'm talking about a minimum energy structure, which is staggered geometry, and a maxima on the potential energy surface, which is nothing but a transition state, which is very, very difficult to trap or capture. This is a transition state. And since I'm dealing with an energy difference between a ground state and a transition state, I call this 3 kilocalories per mole as barrier for interconversion. This is called the barrier for rotation, or I simply call it as a rotational barrier. So this energy difference between a minimum energy structure, let us say this is the staggered geometry, and staggered to fully eclipsed geometry, this is a transition state. That energy difference constitutes a rotational barrier. And associated point to be noted is that this is higher energy. Even though it is 3 kilocalories higher in energy, it suffers from this very, very important terminology, what is known as a torsional strain, where you have your bond pair repulsions. These bond pairs are eclipsing each other. And there are many textbooks which talk about the hydrogen-hydrogen steric repulsion. And I would disagree that hydrogen-hydrogen is not in a position to sterically repel. In fact, if you measure the distance between hydrogen-hydrogen here and that in the staggered geometry, it differs by just about 0.1 angstrom. It's not very different. So the root cause of this, why is it 3 kilocalories higher, originates from the bond pair repulsion. And that term, the BP repulsion, is to be noted. BP repulsion is to be noted as a torsional strain. This is the torsional strain. And we live in a time and age where everyone talks about stress and strain in life, and so are the molecules. Molecules complain when the bond pair come closer, it becomes a strained system compared to the strain-free system, which is staggered geometry. This is the strained system. And remember, this is an open chain system, but strained by about 3 kilocalories per mole. This transition state is strained due to the bond pair repulsion, and that strain is called a torsional strain. Of course, there are other forms of strain, such as angle strain, And then we have this, our most favorite strain of all kinds, of all times, is steric strain, right? One of the most used and misused concept in organic chemistry is steric strain. Okay, and this is something which I tell, and those who have listened to me earlier would have a boring, redundant statement again. If you have a question which appeared in organic chemistry question paper in your final exam, and you don't know the answer to that, but then it is believed and generally stated and told that, you know, you don't never leave a question. The question may be wrong, so you have to write something there. So the condition is what? You have a question, you don't know the answer, but you have to write something. So if you don't know the answer, and if the question is from organic chemistry paper, you would write due to steric strain. This is the answer. Okay. And if the same question as it is, if it appears in inorganic paper, you would say that it is due to d orbital participation, right? So these are two ways of easiest answers to any given problem. There is a solution, because steric is one such way that one would explain. So we are building our concepts upwards, some sort of a projection formula related to structure. There are certain strain aspects to it. One would make a geometry lower energy if it is devoid of strain. I'm just taking a representative and easiest and simplest example to demonstrate that there are various forms of strain. If the system is strain free, then it is a minimum energy structure. And if it has enormous amount of strain, in this case torsional strain, it would increase the energy. That is a property. The energy goes up in the potential energy surface. So these are very, very important points to interconnect. That is one of those objectives which I have for this afternoon, is seemingly disparate concepts, like disconnected concepts studied in chapter 1 and then studied something else in chapter 5, something else in another book, chapter 3. So, you know, one would get into this confusion, what would be the right way to answer this problem? And I would try to make an overarching connection between multiple concepts and tell you how do you look at a problem and what approach is likely to work, okay? Likely to work in a given situation. So with this kind of basics of tetrahedral carbon, a little bit about projection, a little bit about rotational barrier, I have introduced indirectly what is known as an ideal strain-free structure, this versus this ideal strain-free structure, and one form of strain. And now if I take the same concept to another molecule of interest, by cyclizing this, if I talk about cyclopropane, a classic example to illustrate this concept of strain, a classic example for the following simple reason, that in cyclopropane system, saturated cyclic carbon system, in cyclopropane system, all the bonds are fully eclipsing each other. All the CH bonds are eclipsing the other CH bonds. So if you look at this cyclopropane, it suffers from very high degree of torsional strain, and only those who understood what precisely is torsional strain would be able to appreciate this, because this is a molecule which you would never imagine it would rotate in any direction, right? It's a fully planar molecule. It doesn't have any rotational degrees of freedom except the molecular tumbling along its XYZ directions. But within the molecule, there is no rotation possible. It's a locked system. But still, we talk about torsional strain because of this BP repulsion. What other strain it has? It has an enormous angle strain, which is deviating by 49.5 degrees compared to the preferred open chain tetrahedral angle, which is about 109.5. So there is a huge deviation from the preferred tetrahedral angle. And in spite of being an sp3, quote unquote sp3, which is debatable, which can be discussed offline. So a saturated carbon is the best way to describe a saturated carbon cyclic system, sp3 hybridization, but it has a deviation of 45.5. So I'm introducing the third form of strain. I talked about steric strain somewhat jokingly, then torsional strain, and then I'm talking right now about angle strain, a departure from the ideal or preferred tetrahedral angle around a saturated carbon. That departure will also increase the strain of the system. So in regards to steric strain, when atoms or groups come closer than their van der Waals radii, there is a very bad effect. That bad effect is to be understood by first appreciating field-field interaction. Field-field interaction. I will describe this in somewhat more detail. Field-field interaction is bad. Field-field interaction is bad. Okay, this is like that Michael Jackson bad. Field-field interaction is bad. So why field-field interaction is bad? Here comes a little bit of quantum mechanics principle that this is called Pauli repulsion. That is the root cause of steric repulsion. And the steric repulsion is, most textbooks are silent about this. Steric repulsion has to do something with the direction of approach as well. Okay, let me take this trivial example of bringing two phenyl groups. Okay, two independent phenyl groups. They could have gone anywhere in space. If we were to force them to come closer like this, okay, come closer like this, beyond a point, the energy of the system, energy of this dimeric species will shoot up. That is due to field-to-field interaction. Field orbital of this will interact with field orbital of this, the energy of the system will go up. However, if you were to bring these two phenyl groups in this manner, like they are in T-shaped geometry, it would develop a van der Waals attraction, what we call as dispersion bound complexes. It is attractive. So we cannot therefore make a flat generalization that phenyl groups are bulky groups and there is steric interaction. That is where the answers started going wrong, because you didn't appreciate what was wrong with this geometry, and geometry of approach has to do with the field-field interaction. Now, the field-field interaction would be terribly repulsive, because no two orbital can take more than 2 electrons. When I say field-field, I'm actually referring to filled molecular orbitals. Filled molecular orbital repelling another filled molecular orbital. If it turns out to be between two groups, let's say here is a methyl group, here is another methyl group, when they come closer, and if they have to remain closer for even for momentarily, and they would repel each other, because it is all filled orbitals of one methyl will repel the filled orbital of the other methyl, leading to a proper steric clash or steric interaction. And we come across this steric even between hydrogens in what is known as annulenes. N-annulenes, if you remember discussions on aromatic compounds, N-annulenes, depending on what is that N number of pi bonds conjugated, forms a cyclic loop. And if it is satisfying the 4n+2, we call it is Huckel aromatic. And if it satisfies 4n configuration, then we call it Huckel anti-aromatic compound. And where we have even seen the hydrogens facing interior, they have steric clash because they come too close to each other and they go out of plane in an effort to minimize anti-aromatic character. So which we have seen. So it is not that hydrogen-hydrogen steric is never to be talked about. It depends on the geometry. Here in polyannulene or N-annulenes, N-annuline compounds, you can talk about steric. I don't want to draw a N-annuline structure. It is going to take a lot of time. So just to say that if two hydrogens come closer, and they would repel, this will go out of plane, this will go out of plane in an effort to minimize the anti-aromaticity impact. That is a case-specific hydrogen-hydrogen steric, leading to minimization of anti-aromaticity and leading to non-planar structure in an effort to minimize the bad effect produced by anti-aromatic compounds. So we do invoke steric between two hydrogens, but most often for open chain system, it is less likely to have hydrogen-hydrogen steric. The starting point for steric interaction would be between two methyl or methyl and hydrogen and so on. So keep these points in mind, 3 different types of strain and preferred tetrahedral geometry and deviation in angle, deviation in geometric proximity. All these will increase the energy of the system. Now, when we talk about energy of the system, we are quite comfortable with the ground state species that we are familiar with, but oftentimes the energy of a system in the transition state has to be discussed in the context of kinetics, in the context of faster or slower reaction, which is going to be the case as I discussed the actual problems this afternoon. Okay, so now the next task for me is to give you one example to tell you that the manifestation of these steric or these kind of different kinds of strain leading to cyclic compounds taking what is known as a puckered ring structure. It is not that you do not know any of this, you perhaps know all of this, but I need to refresh these in the context of the problems that are going to be discussed. So let me talk about a 6-membered ring. Everyone knows this cyclohexane, and if I ask 100 students to draw their best version of cyclohexane, which could have been a informal exercise if we were in Presidency Hotel, and this afternoon I would have gone around to see how people are drawing cyclohexane in the chair conformer. Okay, so in the interest of saving time, let me draw cyclohexane in the chair conformer. This is a puckered ring structure, and now I can introduce this different substituents on different atoms such that it really looks like a cyclohexane with all its substituents placed at required position. Now, here what is important is to realize when you have different substitutions. For example, if I were to use a methyl substituted or a this is a tetrahedral. So if I use a methyl substituted cyclohexane, all of us know that the axial methyl, this is axial methyl, you can see that this is axial methyl cyclohexane, which suffers from what we call as 1,3,1 diaxial interaction. 1,3. So suppose if I have a methyl group here, to use stereochemical notation and draw it like this. So here is my hydrogen pointing inwards. That will clash with this hydrogen here, this hydrogen here. It creates an unwanted 1,3 diaxial interaction, 1,3,1,5 diaxial interaction. There are, of course, different ways of looking at this same axial methyl, why it is destabilized. One can look at by using different approaches, such as using of gauche interaction. Gauche interaction is another way, quite useful in many contexts. And one can also summarize all these interactions, all this into what is known as a value. And I must also acknowledge that Professor Maitra is the one who taught us A value for first time in my life when I was taking PhD first year course back in IISER days, to be more precise, in the month of August 1996. And I remember walked up to Professor Maitra's office and said that, okay, we Malayalis celebrate Onam. Can I skip your next lecture? I will come back by the weekend. Then he said that today it's Onam, tomorrow it will be Holi, and tomorrow, day after tomorrow, there will be some other festival coming. I cannot give you holiday like that. I decided not to go home. I stayed back and listened to A value of cyclohexane, substituted cyclohexane. Now, what is interesting here is that earlier, in just a few minutes ago, I talked about a rotational barrier. And A value, on the other hand, it's an interesting quantity that will give you an energy difference between G axial minus G equatorial. This delta G is what A value signifies. This is a ground state stability. Ground state stability, that how bad the axial substituted cyclohexane would be compared to the analogous equatorial version. That means if I were to do a ring flip of this, I would get the equatorial substituent. Ring flip of this, I will get an equatorial methyl group. So this will be the position of the methyl group. Then I have I have the system devoid of 1,3 diaxial interaction. You can also show that this system is not suffering from any gauche interaction as well. So this is preferred. So equatorial is more preferred over axial. To extent to which this preference is what is captured in the thermodynamic quantity called A value, which will tell you what is likely to be the equilibrium composition. Equilibrium composition between axially substituted cyclohexane and the corresponding ring flip version or lower energy version called equatorial substituted cyclohexane, when you were to compare this, one aspect one should keep in mind is that this is only about a conformational bias. Okay, this is talking about a conformational bias. Conformational bias, it only is a bias. It is not that this structure is always held fixed in the equatorial conformer. It is not true. It oscillates between equatorial axial. In room temperature, the number of ring flips is quite high. It is to the tune of more than 10,000 ring flips occur at room temperature, with an equilibrium composition of something like 95% of equatorial metal, but 5% is still in the axial. Now, why do I emphasize this? Although I do not have, no, I will not tell you that. Why I emphasize this A value or the energy difference is because there is an interesting concept called reactive conformer. Okay, reactive conformer. And if you have understood this concept of A value and equilibrium distribution is predominantly equatorial conformer, but there is finite presence of axial conformer as well. Finite presence of axial conformer in the equilibrium composition is a very important point to note, because several times the equatorial conformer is not going to be able to give you a product. It is not going to give you a product. And if it is not able to give you a product, then you still find a product. You extract the final reaction mixture, you quench the reaction, you find that product is indeed formed. It shouldn't have formed from the axial conformer. I can give you a very short homework exercise. So if I'm not defining stereochemistry deliberately, if I treat this compound with a base, okay, treat this compound with a base, it can give you a bicyclic compound. And this is one good example to illustrate what is a reactive conformer. A conformer which is higher energy normally doesn't have much population in the ground state, but there is finite population, as I illustrated here. Finite population, that finite population gets more populated, because if you think of this, that this axial conformer is undergoing a reaction all the way to the product, and product is far more stable than the reactant, there is a thermodynamic gain or thermodynamic drive towards going to the product. And if that is the case, what happens is that equatorial reluctantly climbing up to axial, and once it goes to axial, it can go to the product. It is easy to go to the final product, and such things are a situation where one would have to invoke this idea of reactive conformer. And oftentimes reactive conformer could be in a board structure. It could be in a geometry where the substituent is held in the axial position. So it is not like prevented from going to axial, because if you have an appreciation for what is A value, it only talks about the extent of the bias that is present, but it does not talk about just zero concentration. Even T-butyl, okay, T-butyl is the worst of the substituent that one can think about. If I dare to show you a structure, T-butyl, let me attempt to make a T-butyl here. So here it is. Yeah, so this is a tertiary butyl substituent on cyclohexane in the axial orientation. This is terrible. This is way more terrible than one can imagine. And you can work out how many bad Gauss interactions are present in this. And it is clearly a steric interaction between the methyl and hydrogen. You see the proximity between methyl and the hydrogen, which was not the case for any other substituent in the axial. So T-butyl axial is very bad, and it is perceivably bad. Nevertheless, there is 0.01 population as per the A value. Thermodynamics suggests that there is still 0.01 population of T-butyl axial orientation. Now, this is important because this has implications in some of the problems which I'm going to discuss, and I hope it won't misguide you, because I told that T-butyl can also become axial. It should not, destabilize the problem. It is all the time equatorial, but there is a finite chance that as per A value, it could even go through axial T-butyl. The point to be again noted is that even in T-butyl substituted cyclohexane, there is ring flip that is happening. And if the ring flip has to happen, it means that there is an equilibrium with a huge equilibrium constant favoring the equatorial version, but there is an equilibrium between axial and equatorial. That is the take-home message from the structure geometry perspective of this part of the discussion. So what is the take-home from the T-butyl? Take-home from T-butyl is the following, that if you have a T-butyl substituent, it prefers the equatorial orientation. So hereafter I will draw like this, and then we are going to discuss a lot of chemistry at this site, that is 1,4 relation. This is carbon 1, 2, 3, 4. And we're going to discuss a lot of events over here by installing different substituents when we enter the problem solving section of today's lecture. Now, so the next property of interest that I'm going to talk about is introduce very briefly some of the building block molecular orbitals which are highly relevant towards understanding organic reactivity. Okay. So it is not just about the structure. There is inherent attributes which molecule carries with it, like be it a saturated system, unsaturated system, double bonded system, whatever you would come across in organic reactivity, there is an underlying set of molecular orbitals that is to be understood. And now, if you were to look at the molecular orbital for ease of discussion, let me just bring two p orbitals and bring them in a head-on manner and combine them to form a molecular orbital. We call it sigma bonding molecular orbital. This is the essential feature of a carbon-carbon sigma bond. So if I were to overlap these two molecular orbitals, atomic orbitals to form the molecular orbital, then I would get a bonding molecular orbital. This is a BMO bonding molecular orbital, and this is a sigma bonding molecular orbital that is responsible for the carbon-carbon sigma bond, which is formed as a result of head-on overlap along the axis, and it is a very strong overlap with a huge degree of overlap integral. And this could also be written as a significant overlap between the internuclear distance, internuclear direction, and a small lobe of opposite phase pointing away. These are equivalent representation of bonding molecular orbitals. Okay, so this is sigma bonding molecular orbital. Now, this is in phase combination. I would also have to do an outer phase combination to construct what is known as a anti-bonding molecular orbital. So most textbooks, I would say many textbooks write this wrong or sketch this wrong. Let me clarify what is and where is it goes wrong. Remember, this is a repulsive interaction between, they are out of phase. It is a repulsive contact between nucleus 1 and nucleus 2. And this is a anti-bonding molecular orbital. And what we short form is sigma star, let's say carbon-carbon bond. Sigma star carbon-carbon bond. And this sigma star is an empty orbital. This is extremely important for both today's discussion and for your take home. This is an empty orbital which is present wherever there is an occupied orbital present. So this is occupied, this p electron, there is one p electron from here, one from here, and doubly occupied molecular orbital is sigma. So sigma is doubly occupied, whereas sigma star is unoccupied. Sigma star is unoccupied. This is an empty orbital. And the fascinating aspect of this empty orbital is that a lot of chemistry, a lot of reactions, a lot many more properties of given molecule is by virtue of having this feature, this characteristic of empty sigma star. This characteristic of empty sigma star. Remember, whenever you want to break a bond, break a carbon-carbon bond, which is true for many, many rearrangement reactions, right? Yeah, you have drawn ring contraction, ring expansion. I have one beautiful example this afternoon. Ring contraction, ring expansion. There are two ways to break a bond. One is to make the bond order 0. How do you make the bond order 0? Give 2 electrons, which is already there. If you have a way to put 2 electrons into this antibonding molecular orbital, the bond order would go to 0. That means you are converting this 0 occupancy to double occupancy. Then you would be in a position to make the bond order 0, and the bond would rupture, bond will cleave, bond will break. Correct? So if you want to break a bond, as simple as the reaction which Professor Maitra discussed yesterday, if you want to break a bond, let me bring in a nucleophile in one of your most favorite reactions, that is SN2. There was quite a bit of discussion yesterday, SN2 reaction. So let me, for convenience, let me use this hydrogen and 1R group here, a primary alkyl halide. The living group, it could be tosylate, it could be any favorite living group which you may want to choose. Now, in this event, I bring in an incoming nucleophile, I push these electrons onto this carbon, break the Cl bond. If I have to break the Cl bond, what is going on? And I would ask one step further, I will ask, what is the accepting orbital? So I'm bringing in the concept of donor acceptor language in organic reaction. So I'm bringing in this new way of looking at, it's not new way, but it is a way of looking at organic reactivity problem by invoking the idea of molecular orbitals from a donor orbital to an acceptor orbital. So if I use this electron double-headed arrow pushing in 2 electrons, if I ask this question more precisely, what is my accepting orbital? The fact that carbon living group bond is broken as a result of this reaction, it is the sigma star which acts as the acceptor, so that the bond order of Cl is going to 0. And if this has to happen, then the acceptor orbital should be facing the incoming nucleophile. It should be facing the incoming nucleophile. So if I were to include this sigma star nature of this orbital, this is how the sigma star orbital is, right? Sigma star, I have just drawn here, carbon living group bond. This is the sigma star. You look at where is the largest coefficient or largest region of that orbital. The orbital is right here, away from the carbon living group bond. It is on the opposite side, and this is the one which will accept electrons to it. That is, the sigma star empty orbital is responsible, and that is precisely the reason why you have a backside attack in SN2 reaction. The backside attack is because it is towards the backside that sigma star is pointed to, and it gets the accepting accepted electrons. So now one aspect about nucleophile, let me say, if my nucleophile is, it's a bad example, but let me bring that. If the nucleophile naturally, which would have lone pair of electron, water is not going to be able to do an SN2, but just to bring home a familiar entity. So it has lone pair. In lone pair, in molecular orbital language, lone pair is equivalent to a non-bonding molecular orbital. Lone pair is equivalent to a non-bonding molecular orbital. The fact that it is loner, no friends, staying alone, right? Fact that it is lone pair, it is not participating in any sort of bonding in the native molecule. What is the native molecule? Ammonia, water, cyanide, iodide, all these guys, they have lone pair, excess lone pair, and they are not participating in any bonding. Therefore, this is non-bonding. It resides in non-bonding molecular orbital. If you want one more example, a good one would be to think about BH3 kind of species, which has NTP orbital. So this is an unoccupied orbital, as part of a molecule. Therefore, we call this as NBMO, non-bonding molecular orbital. This is just a terminology fact. Okay, so non-bonding molecular orbital, as in the case of lone pair, could be occupied, or as in the case of BH3, could be unoccupied. So I have introduced 3 sets of orbitals. A summary of it is here: sigma, sigma star, and I have talked about non-bonding. I will represent using a small letter n. Now, what I'm going to do, if I refer to ethene or ethylene, I also have a pi bond formed by lateral overlap between 2 p orbitals. So this is my pi C double bond C, doubly occupied, and the corresponding antibonding molecular orbital of pi would be pi star, which has 1 node here and so on. So I represent this as pi star, carbon-carbon, but unoccupied. So this is a ABMO with regards to the multiply bonded carbon-carbon system. So there is a sigma bond, there is a sigma star, there is a pi bond for ethylene, there is a corresponding pi star for ethylene. If you know all these 5 sets of molecular orbital, the way you would look at organic reactivity problem, the way you will look at the stereochemical outcome of a reaction in an organic chemistry book or organic chemistry learning process, the way you would look at would completely transform. Because thereafter, you would always look for what is my donor orbital, what is my acceptor orbital. I always tell my students, the freshman chemistry students, BTech students, or BS students in my department, or MSc students in my department, I always tell them that if you think that organic chemistry is a memory-based subject, I don't fully agree with that. It is a reflection of the fact that you missed many concepts. You missed many concepts and you try to enforce this into your brain and try to memorize. You don't have to memorize a lot of things, provided you approach the problem based on this donor acceptor orbital language. A lot of reactions would appear very simple. Whether it is a nucleophilic addition on a carbonyl and a ring expansion and contraction, all those would appear very, very simple and very straightforward. So now I have to move to some of the problems. Let me share the screen. Joshi, how much time I have?
Sunoj, you have 15 more minutes.
Okay. All right. So I'm going to, so the summary is that we have molecular orbital. We discussed different forms of strain. We discussed the tetrahedral geometry. We discussed a little bit of conformers. And with that background, let me see if I can apply some of these concepts into reactivity, and a set of these concepts into give me a second, because the screen, I just have to do some adjustment. Okay, so here it is. And I request students who are listening, please look at this question. I am not even told what is the question, but you could identify what is the question by spending a few minutes. I will complete the question. If you can walk along with me in addressing this, that will be very nice. It will be very beneficial to each one of you. So first you note down the structure. There is a, so I'm switching gear. I'm going into the problem solving mode. So there is a ester group here, right? There is an ester group which undergoes hydrolysis. Ester undergoes hydrolysis to a carboxylic acid group. So reaction is simple. Okay. And this is, let's say, base hydrolyzed under basic condition. The hydrolysis happen. Now, the question is, so you have to, sing along. The question is, if this is ester A, okay, so this is my ester labeled A, which can exist in two diastereomeric form, because I have not defined the stereochemistry at this carbon or stereochemistry at this carbon. So it could have, A could have cis 1,4 compound or trans 1,4 compound. I hope you're able to follow what I'm saying. Since I have not defined the stereochemistry at these two carbon centers, it could be a cis geometry between 1,4. They could be the substituents such as T-butyl. Hydrolysis with one of these diastereomers, cis or trans, is 20 times faster than the other. 20 times faster than the other. Why? One of these is faster than the other 20 times. Why? Is cis faster? So we could start with the hypothesis that cis is way more faster in hydrolysis than trans, or the other hypothesis would be that trans is way more faster than cis. So this is these are two ways to approach this problem. So I'm sure people are beginning to think about it. Now, I will give clue number 1. Draw the chair conformer. That is where you start. Draw the chair conformer. In a non-interactive mode, it's difficult to gauge what people are doing. Whether there are not many people sleeping or not, I do not know, but I have to assume, make assumptions and proceed. Okay, so I'm sure that some of you have drawn the chair and board, chair structure. So if I were to draw the, let's say, one of the chair forms. So this is my one possibility, and the other one is when this ester group is axial. Right? So these are two possibilities. These are the two diastereomers. Let me call this A, diastereomer A, and this is diastereomer B. The question is which one would react 20 times faster than the other. So how do we approach the problem? And when we say 20 times faster, naturally it has to do with the transition state, which is more preferred transition state or lower energy transition state. And the approach that one would see here is that you have to look at the tetrahedral intermediate, because this is OH minus base catalyzed hydrolysis. So OH minus is going to attack this carbonyl carbon, and it produces a tetrahedral carbon. And then you would write the intermediate, or you would propose a tentative structure for the transition state. So let us look at this in the following manner, that you have a a large group in the axial position versus you have a large group in the equatorial position. That's what the problem is boiling down to. And I have discussed earlier that what do you expect when the substituent is at the axial position and what do you expect when it is in the equatorial position. So you should put this logic together that will help you understand which one would give you a lower energy transition state, and that is the one which would react faster. Unfortunately, there is no way to interact. So let me see. Are there responses? Okay, so there is no response to this problem. So let me then move on to the next question. So here, the one which would have the axial ester in the axial position, there is a ground state destabilization. So you would have proximity. So if you compare energy of this is higher compared to this is energy of B and this is the energy of A, and you're talking about a transition state energy, and you're talking about a transition state, let's say transition state energy here. So this is destabilized. There is a ground state destabilization works in its favor, and the cis conformer where the T-butyl and the ester on the same side. So cis conformer, cis diastereomer, that is compound B, diastereomer B would react much faster than compound or the diastereomer A. That is one way of looking at. There are multiple aspects that are put together here. A, the conformational bias created by the T-butyl group. Otherwise, you could have had many more conformers. So T-butyl would bias the ester in the equatorial or axial by holding the ring in a position like as shown here with A and B. And then it's a question of the donor acceptor orbital, which is not directly relevant, but you can explain why this transition state is higher energy, etc., by using some of these ideas. So the donor orbital is non-bonding on oxygen of hydroxide, donating to the pi star and debonding of carbon oxygen bond, which is empty. So this is a shorthand notation that you can use for bringing up the electronic argument, what triggers the formation of the tetrahedral intermediate from this trigonal carbon. So what is happening here, if I may write this ester group, this is the actual process. So you have, let's say, OCY, cyclohexyl group, and this donor orbital from hydroxyl will attack this carbonyl carbon, which is electrophilic carbon, and which will produce a tetrahedral intermediate. This will become an alkoxide, and you have the hydroxyl group here, and you have the OCY here, and then you have this OET, which is actually a good living group. And now you can push this in and bring this out, and you form this carboxylic acid group, and that will explain the total mechanism of this process. So you can say that this is the final group that would be formed. So OH is the new group which is installed as a result of nucleophilic addition of OH in the base catalyzed process, and that is the way you would be able to understand. Now, why do I bring up such an example? Is to show that to show and illustrate the comparison that if you come across this as a question in any context, okay, competitive exams or in a final year exam, here you're not scratching your head as to whether you have learned it before or not. So what you have applied here is a very simple set of concepts that the concepts applied here are the following. The donor-acceptor interaction. Because what is my nucleophilic partner or donor? It is clearly the OH minus. That is my nucleophilic partner. What is my electrophilic partner? We all know a carbonyl group of this kind, due to differing electronegativity between these two connect and you. So imagine that this is a brand new question. You have not come across this. You don't even know what is ester hydrolysis. Still, the approach that the way you would learn is useful to tackle this problem, that there is something about conformer, bias, nucleophile, electrophilic end of the molecule or electrophilic region of the molecule. You're combining all these concepts together, but not taking a major section from your memory, right? So this is the problem solving approach which I would like to emphasize. And in the next question, which I would describe is, okay, so here is the question. This can be viewed as a mechanistic question to begin with, but I have an orbital interaction problem associated with this. Given the time constraint, I think this is the last question which I would describe, is the product of the following reaction. Reaction is shown on the slide. The product of the following reaction leads to a monocyclic ketoalkene. A monocyclic ketoalkene. Identify the orbitals involved in this transformation. So identify the orbitals involved in this transformation. Identify the molecular orbitals involved in this transformation. So if you look at this problem, the product is not clearly described. It monocyclic alkene. So one can think of multiple ways and get lost also. So therefore, let me, in the interest of time, let me just describe a little bit in the form of a clue. You try conformational diagram. That's going to help you understand what are the likely orbitals that are involved. So if I help you by giving this clue, if I push these electrons here, that is O minus, break this bond, move this electron here, and this OTS is a grade leaving group. And if OTS leaves the system, this would be a very good lead for those who are smart enough to solve it, and those who want a little bit of hand holding, I'll be happy to do. But I would like you to first draw the conformational diagram, without which this problem is not going to be complete. So in the interest of time, let me draw the conformer. Why did I draw like this? You can understand this because I have this hydrogen above the plane and I have this O minus below the plane. So therefore, I'm talking about a trans geometry at the ring junction, between, let's say, A ring and B ring of a bicyclic framework. Okay. And the product is monocyclic. That is a clue that is given. And O tosylate is above the plane. So it should be an equatorial substitution as shown here. Now, if I look at the mobility of electron from here to here, and this central bond is broken, and central bond is broken is a lead clue connecting us to monocyclic system, from a bicyclic AB system to a monocyclic system. So that also gives a very lead clue for proceeding further. Now, the third and last aspect of this is that the fact that there is a bond broken, the bond that is broken is clearly the central carbon-carbon bond, or the bridging between A and B is broken. So if you have to break a bond, it is better that we break the sigma bonded molecular orbital between these two carbons. So I would draw the sigma bonded molecular orbital in this manner. And OTS bond is broken, so it is the sigma star of interest. So I will draw sigma star in this manner, and sigma star will be drawn like this. You see the shading, the way it is changing. And now this transfer, what you are showing is as using conventional arrow like this, conventional arrow as shown here, that is due to a lateral overlap between the CC sigma of the bridge position, CC sigma donating to COTS sigma star of COTS MT, and this is the right way of looking at it. Okay, this is the orbital interaction responsible for the rupture of the central CC bond, that is the CC sigma that would be broken because of this electron transfer. Now, the last aspect of this question is that the monocyclic, if it was in a real classroom, I would have helped you with this. The monocyclic alkene with a trans double bond is what is formed as the product. And if you were to look at this, why is it trans double bond? You see this hydrogen above the plane, and there is this hydrogen below the plane here, and the double bond that would be formed as a result of completion of this entire process would be, the completion of this process will lead to hydrogen which is at the ring junction before, and this hydrogen is below before the reaction. It continues to be below before the reaction, and a new double bond is formed. And this is the monocyclic product that is formed, and this has a trans relation between the hydrogen. It's a large macrocyclic, reasonably big large cyclic system, so you can afford a trans double bond as well as part of the system. So these are just representative examples to show that how the concepts can be interrelated: structure, orbital, conformation, relative energy, transition state, preferred versus less preferred, and alignment between sigma star as an accepting orbital with respect to any donor orbital. So this was basically what I intended to discuss with you. It could have been better naturally if it was a real, classroom, but then we have nothing much to complain. At least FCBS is on this year. I'm very glad that I could be part of this. And I think my time is up. Thank you very much for listening.
Thank you, Professor Sunoj. And I think in chat box, there are a couple of questions and some responses about the question you are asking.
Mm-hmm.
The first question is from Rohini S. Among the three strains you have mentioned, which one will make a system more unstable in magnitude, actually? I mean, just which one, the magnitude she want to know, I think.
Okay. I think the inherent destabilization should originate from angle strain, which is unavoidable. You can have ring puckering, some sort of a dynamics to be able to relieve some of this strain. For instance, cyclopropane, there is no way to relieve the strain. But when you go to cyclopentane, cyclohexane, it can go to non-planar structure, which would minimize the angle strain as well as torsional strain. So in the progressive order of magnitude, I think the angle strain would be a dominant factor for smaller rings, and angle strain reappears for much larger rings as well, because it works the other way around. The steric strain, to certain degree, it can be overcome by conformational flexibility if it exists in the system, and torsional strain is due to a rotation of some kind, or due to the fixed position, which could be avoided if there are alternative conformers possible. So it is a mix of these factors, but unless there is a system to system comparison, molecule A to molecule A dash, it is rather difficult to make a generalization. That would be the way I would respond.
Yeah, there is a comment from Professor Uday Maitra. Sir, do you want to say something about it? It's still there.
No. I just wanted to point out that, of course, for the carboethoxy ester, the rate ratio is about 20. Mm-hmm. While the structure you drew was a propionate. There also the rate ratio will be in favor of one of the isomers. but it will be about 3 or so, 3 to 4.
Okay, it should have been methyl instead of ethyl.
Yeah. So,
No, I think you first mentioned the carboethoxy group, the carbon attached to this thing, carboxylic acid ester.
Oh, right. Yeah. So I had two related questions. That is why the mix-up.
I know.
Because I wanted to extend one atom away. Yeah.
Exactly.
Yeah.
So I just wanted to point that out. Yeah.
It should just be about 3. Yeah.
Yeah. It's the same order, so it doesn't matter really.
Right. Yeah. Cis is still preferred faster. Yeah. The 20 rate acceleration, you have to have a direct connection. Yeah. Not with an intervening oxygen. Yes.
Exactly.
Yeah.
I think many of them got confused because of the structure, a little bit change in the structure you've drawn and the question. So, I mean.
Oh, okay.
And the next question is from Ranjit Thomas. There are several arguments for explaining the relative stability of staggered ethane over eclipsed ethane, like steric effects, electronegativity, hyperconjugation, etc. Which you think will be a more correct approach? Thanks.
So ethane is a debated topic, but certainly not steric. Bond pair repulsion is a reasonable one, but that would only explain the destabilization in the eclipse geometry. Bond pair repulsion is silent when you go to the staggered geometry. So when you go to the staggered geometry, one of the reasonable interpretation based on molecular orbital argument is that you have a anti-periplanar sigma CH and sigma star CH, anti-periplanar. So they have a parallel arrangement with respect to each other. So that is an alternative interpretation that will help one understand. So I'm talking about this sigma, CH sigma, and a sigma star, which would have a larger lobe here and opposite interaction here. So this lateral overlap, a feeble donation, very weak, but there are 3 of these in the what you call as the staggered geometry. Staggered geometry has this sigma CH to sigma star CH delocalization. Okay, occupied to unoccupied, but this is a very, very weak delocalization, 3 in number. So this will explain why the staggered is a little bit more preferred over the eclipse. So eclipse has one problem, which is BP repulsion. Staggered has an advantage of being able to delocalize to the anti-periplanar CH bond. So the combined effect is what you see as the energy difference. So that is the latest version of, this is back in early 2000 is what the molecular orbital interpretation was introduced. If you were to look at the extreme of this, if this delocalization is complete, you're acquiring a partial double bond character, because you see this lateral overlap, and partial double bond character would lead to a situation called no bond resonance, which you would have come across, where this will become hydride, this will become proton. These are extremes, not to be taken as a major factor, but a feeble delocalization is reasonable to assume. That's my stance on this. Why staggered is lower than eclipse? Because of these 2 factors. One, additional stabilization due to a little bit improved delocalization. The other one is bond pair repulsion, not certainly the hydrogen steric, because they are far away to afford any steric interaction. They are not even pointing towards each other.
Okay, so one last question for disubstituted cyclohexane. Is the stability changes by changing position? That is, I mean, the cis and trans stability.
Yes, it does. Because different reason, because these groups are too close to each other, whereas they are a little bit farther, and these 2 are farthest. So yes, stability order is not identical depending on the position of the attachment. For 1,2 disubstitute, it changes. And one more rider here is that what are those groups attached is equally important. If you have a heteroatom, for example, here a lone pair bearing atom, the stability order is different. If you have a phenyl, stability order is different. So there are many contributing factors, a mix of steric versus electronically active versus electronically inactive substituents. All this will play a role in deciding which is more preferred.
Okay, I think at the interest of time, we will stop the discussions here. And I have shared the Professor Sunoj's email ID in the chat box. So please post your questions. He will be very happy to answer your questions by email. And I take this opportunity to thank Professor Sunoj for that wonderful lecture. Every year we get the pleasure of hearing your talk. At least that 1 hour is never enough. And I understand that in the meantime, you are giving different talks in different colleges, extended talks, which is very helpful for our students, especially these kind of things they miss even during their MSc classes. Thank you. Thanks a lot, and see you again.
My immediate next lecture is in Calicut, end of the week, but that is on quantum mechanics.
Okay. Okay.
Thank you.
I think the Kerala chemistry teachers are well connected. Any talks, any part of Kerala is widely publicized, so they have enough.
Yeah, but the topic is very different, not organic.
Yeah.
Okay.
Okay. Okay. Thank you. And with this, we will move to the next talk of today. Thank you, Sunoj. And next talk is by Dr. Vijay Kumar. Vijay, you can share your presentation.
Yeah. Thank you, Joshi. Can you see the slide?
Not yet. Okay. Meantime, let me give a short introduction to Vijay Kumar. He is a senior scientist in CSIR-NIIST Trivandrum, and he has completed his PhD also from CSIR-NIIST Trivandrum around 12 years back, and did postdoc in Japan, Tsukuba in NIMS. And he is also a very vibrant organic material chemist, I should say, doing a lot of very good research work and publishing very good papers. And he is a recipient of recent Kerala State Young Scientist Award in 2016, actually, and a recipient of prestigious Ramanujan Fellowship. And with this introduction, let me welcome Dr. Vijay Kumar Sinayar for the talk. Thank you.
Very good evening to all of you. So Joshi, the slides are visible.
Yes, Vijay, you go ahead.
Okay.
I will let you know in 50 minutes, okay?
Okay, yeah, thank you. So good evening to all of you. And today I'll be talking about a synthetic class of material called halide perovskites. So this is actually a different topic what Professor Sunoj was discussing. So we are basically moving from out of organic chemistry to material chemistry. And this is a class of synthetic materials. And among material chemists and device physicists, it is called as a wonder material because of its unique optical and electronic properties and its widespread applications in optoelectronic devices, especially in photovoltaic devices. So in the next 45-50 minutes, I will discuss about this material, why it is so unique and what are the major properties of this material and what are the major advantages of this material. And there are some challenges also associated with it, that also I will mention. And along with that, I will discuss some of our recent research in this area, some of the research we published in this area. I will quickly mention those also. So before going to the details of the talk that is on halide perovskite, I would like to give a brief introduction to this area. So initially, I will be talking about the inorganic perovskite or the rock solid perovskite. That is the traditional perovskite which is available in the earth crust. That is a plentiful mineral available in the earth crust. This is also called the perovskite oxide. Actually, I am talking about a different class of material, but that also belongs to perovskite. That is halide perovskite, and the slide I am showing is on the perovskite oxides, because that class actually developed from this topic. So as I mentioned, it is a plentiful mineral available in the earth crust, especially the silicate-based perovskite, and it is mostly seen in the Ural mountains of Russia. The first perovskite was discovered in 1839. That was the calcium titanate. The structure is shown here. I'll take the laser pointer. You can see the calcium titanate structure here. Here it is the calcium CaTiO3. It was discovered in 1839, and this is a typical perovskite structure. You can means perovskite solid, rock solid. You can see this cubic structure is actually the perovskite mineral. And this calcium titanate was discovered by Gustavo Rose in 1839. He was a German mineralogist, and he named this material, this calcium titanate, as perovskite to honor his fellow mineralogist from Russia, U.A. Perovsky. So that is the beginning of the story of perovskite, that begins with the calcium titanate. And any material which is having a structure similar to that of calcium titanate can be called as perovskite. So it's a large class of material. A huge number of materials are there. Any material which is having a structure similar to that of calcium titanate. So it is very simple to remember. You just need to remember the structure of calcium titanate, and any structure which is having a similarity with the calcium titanate can be called as a perovskite, whether it is a naturally occurring material like perovskite oxide or a synthetic material like halide perovskite. Doesn't matter, you can call the material as perovskite. Okay. And this is the structure of a typical perovskite material. It can be represented like ABX3, and it is having a structure like this. A is a metal cation like calcium, potassium, sodium, etc. B is another metal cation like titanium, lead, tin, strontium, bismuth, etc. And X is a oxide anion. This X oxide anion forms a octahedral structure like this, and the B cation occupy inside the octahedral structure, forming a structure like this. And these octahedral structures are joined together to form a three-dimensional structure like this, and it grows in 3 dimensions. Okay, and the void formed by the growth of this three-dimensional structure is actually occupied by the A cation, and this is actually needed to neutralize the charge in this whole structure, and this whole structure is a neutral structure. And because of the positive charges from the A metal cation and the B metal cation and the negative charges from the oxide ion, this material is charge neutral. Since, as I shown here, many metal cations are possible to occupy the position A as well as position B, we can get a variety of perovskite structures, and we can also do a lot of engineering on the material structure to get different kinds of perovskite structures and different perovskite properties. So depending on the atoms we are using in the structure, we can have very impressive and interesting properties for this material. So depending on the application, we can actually select the A cation and B cation, and depending on that structure, you will get the corresponding properties. And these are the major properties summarized here, that these materials show excellent magnetic properties, especially magnetoresistance properties, because it can switch the electrical resistance in the presence of an external magnetic field, and that is very useful for making optoelectronic devices and optical and electrical switches also. And these materials show very good ferroelectric properties, piezoelectric properties, electrical conductivity, ion conductivity, superconductivity, catalytic properties. So you can see most of the materials, most of the properties of different materials are actually shown here, means expressed by this particular single material. So because of this variety of properties and excellent properties, this material can be used as sensors, capacitors, electro-optical switches, electrode materials, memory devices, fuel cells, and catalysts. So that is why this material is called a wonder material, because you can have get a large number of properties that are also extremely high properties, not just mediocre properties. You can get the best in class properties from this material. And similarly, it can be used for a variety of applications. A few only I represented here. But these materials doesn't have the semiconducting property, and which is very essential for the photovoltaic application. So the perovskite oxide be like tin or lead or strontium or bis. Instead of oxide anions, here you have the halide anions like iodide, chloride, or bromide. And this is again forming a octahedral structure like this, with the halide ions occupying the corners of the octahedron to form a BX6 octahedron, and several of these octahedron joined together to form a three-dimensional structure. And the void formed by the formation of the 3D structure is occupied by the A cation. It can be an organic cation. Normally, if you want to make a three-dimensional perovskite, the size of the cation is very, very important, because the void size is very limited. So you need to select either methyl ammonium cation or formamidinium cation. These are the two possible organic cations if you want to make a 3D perovskite. And in addition to that, you can also use a cesium cation for the same purpose. But if you are looking for other class of perovskite like layered perovskite or one-dimensional perovskite or zero-dimensional perovskite, you have a large possibility or large selection of organic cations that you can select depending upon the properties you want. And these halide perovskites are considered as the golden boy of the next gen light emitting diodes, sensors, and photodetectors, because these properties, as I mentioned, it is very unique. The optical and electronic properties are very unique, and these materials are giving a very good solar cell efficiency, which is comparable with the silicon solar cell. And similarly, it can give very efficient light emitting diodes and sensors and photodetectors. And this is, as I mentioned, it is mainly due to a lucky combination of unique optical and electronic properties. And in addition to that, these materials are very cost effective, because these are abundant material in the earth, and the processing is very simple. It's solution processing, and because of these combination of this lucky combination of unique optical electronic properties along with the cost effective processing, it created the basis for a perovskite revolution in the last few years. Because of that, it is very important for a chemistry teacher or a chemistry student, not only chemistry, a material person also. It is very important to know something about these materials. And it was the halide perovskites was first synthesized by Professor H.L. Wells in 1893. So that is more than 1 century before. And he did comprehensive studies on the synthesis and some of the properties of the lead halide perovskite, mostly using the methyl ammonium or cesium as a cation. But it was only an academic interest at that time. And later in 1995, almost 25 years back, Professor David B. Mitzi in Duke University, USA, he did some more analysis or some more, he developed a few more materials in this class. And he did some other characterization of these materials, and he also studied some of the properties of this material. But even at that time, it is only an academic interest, and there was nothing unusual about this material, because people didn't try to use this material for the optoelectronic device application. But later in 2009, Miyazaki and co-workers was actually looking for a alternate for the ruthenium dyes. They were actually working on dye-sensitized solar cell at that time, and they were looking at a replacement for the ruthenium dyes to get better efficiency, because it was kind of saturation at that time, maybe around 9 to 10% of efficiency they were getting for the DSSC cells. And they think that if they have a better absorber for the photons, it would be possible to increase the efficiency of the DSSC cells. So that is why they were looking for a new material, and they found that these halide perovskites might be suitable for using in DSSC devices, because these materials can show excellent absorption properties. So they selected methyl ammonium lead halide, lead bromide, as well as lead iodide. And they used the traditional liquid electrolyte based DSSC. So they were basically using the triiodide based electrolyte. Actually, it's a very corrosive electrolyte, and these halide perovskites are ionic in nature. And because of the mismatch between the basic or the fundamental property of this electrolyte and the material, actually the devices were highly unstable and the performance dropped rapidly within few hours. And though they were getting efficiency like 3.8 in methyl ammonium lead iode and excellent VOC like 1 volt, it was not enough because the performance dropped rapidly because of the interaction between the corrosive electrolyte and the perovskite material. So it was not really successful at that time, and they dropped that idea to use this material as the absorbing material in the DSSC devices. But later in 2012, Professor Greitzel and Park was again, they were actually the pioneers in dye-sensitized solar cells, and they were again thinking in the same line and thought about using perovskite as the light absorbing material. But instead of using a liquid electrolyte, they thought that it cannot be used for this purpose because of the same reason it is corrosive. So they thought of using a solid electrolyte, solid whole transport material called spirometers, and they found that this perovskite is giving very good efficiency. It is exceeding 9%, and in addition to that, it is giving a very good stability also. Unlike the electrolyte-based, liquid electrolyte-based DSSC cell, this solid state, complete all solid state DSSC was giving very good efficiency, which is exceeding more than 9%. And that was the real breakthrough happened in the research of halide perovskite. So students can note down this year, and researchers who did the breakthrough in this area, those are Professor Greitzel and Park. Breakthrough paper was appeared in scientific reports in 2012. And later, many people started working in this area from different parts of the world. Now there are hundreds of research groups fully dedicated for the research in halide perovskite, especially for the solar cell device application of these materials. And because of that collective effort by hundreds of or thousands of researchers all over the world, the device efficiency of this material close to 25%. Now the recent studies showed that, or the NREL chart shows that the efficiency reported by a Korean lab is around 25.5%. So you can see other solar cell devices efficiencies were compared in this chart. You can see whether it is a multi-junction cell or single junction cell or silicon based single crystal silicon, or with the concentrator or non-concentrator or multi-crystalline silicon, or other thin film technology like CIGS or CGT or amorphous silicon, or even the emerging photovoltaic devices. They actually took several years, or you can say several decades, to get a very reasonable efficiency. But in the case of perovskite solar cell, researchers were able to get this very good efficiency, like more than 25% efficiency within like 10 to 12 years. So that really reflects the capability of this material, and still there are a lot of options to improve the cell efficiency, either by doing engineering in the material part or by doing engineering in the device part. And several research groups as well as industries are involved in this research and development, and hopefully we can see much better efficiency in these materials. So why we are getting very good optoelectronic properties and exceptional high solar cell efficiencies in this material? Because we are actually getting the best of both worlds. This is actually for the these efficiencies were mostly reported for the methyl ammonium lead iodide. Okay, so here you have the organic component as well as the inorganic component. This organic component is actually the soft part of this material, and the inorganic component is the hard part of this material. So you cleverly combine the soft part and hard part, and this soft part actually can give good solubility to this perovskite material, and it can facilitate self-assembly to form very ordered structure, and that also help this material to deposit from solution. So that is very, very important. In the case of normal devices, especially the silicon-based devices, you need a highly expensive fabrication facility to do the vacuum deposition or other kind of deposition techniques, because it's a high energy process, a high temperature process. But in the case of halide perovskite, it is a room temperature process, and you can do it in as a solution process. So it is very, very effective, and this property is actually coming from the presence of the organic component, because it can give very good solubility to the perovskite material. It can impart self-assembly to this material, and that is very, very helpful for the for making these films, thin film for the device development. On the other hand, the inorganic component or the hard part of this material, that actually enable or provide a very extended network by the strong bonding interaction between the inorganic clusters, and which results a very precise crystalline structure in these deposited films. And this is very, very important for the very smooth charge transport in this material, because normally if you have a organic component, just have an organic component, normally whatever the higher ordering you are able to get, the charge transport will be very, very poor normally. Okay, because there will be a lot of defect site will be formed in this material, and that will effectively act as trap in this material, and that will pull down the charge carrier mobility and charge carrier transportability of the material. But in this case, the charge transport is mostly happening through the inorganic framework, and it is very, very strong and very stable, and the possibility for defect formation in that part, in the inorganic clusters, is very limited, and that actually considered as an express way for these charge carriers to move along the material, and that really helpful for this material to show very good device performance. Okay, so we are basically getting the best of both worlds and the best of the inorganic part. So in addition to that, I mentioned in the previous slide, these are very low cost material because these are earth abundant. All the materials we are using earth abundant, and because of that it is very low cost, and the synthesis is very easy. Anybody can do the synthesis in a college laboratory or in almost anywhere. And another important thing is scalability, because even if you are getting very exotic properties from any material, if it is not scalable properly, then it is not useful for the real world application. But in this case, you can actually make a kilogram scale or even ton scale very easily, because these are very, very simple reaction, and they show intense absorption and sharp emission. Okay, normally you won't get very good charge carrier transport properties or the charge separation properties, which is essential for the solar cell application. At the same time, the same material, you cannot get very good emission, because these are two different properties. And as the rule of thumb, if a material is suitable for the solar cell application, it cannot be suitable for a light emitting diode application. Okay, but in this case, the same material can be used for the solar cell application as well as for the light emitting diode application, because you can get the charge separation in one kind of material like a 3D material, but you can get a very, very sharp emission if you can confine the material within the nano scale. Okay, so if you can impart quantum confinement in this material, you can get a very sharp emission also. So this material shows not only intense absorption and sharp emission, and that is mainly associated with the highly symmetric structure. And because of the highly symmetric structure, they're actually having a direct band gap, and because of the direct band gap, the absorption is very intense. And this is the band structure of the methyl ammonium lead iodide, which is the conduction band is formed by the antibonding orbitals of lead P and SNP orbitals of iodide. And the valence band is formed by the antibonding orbitals of lead and lead S and iodide p orbitals, and it can give a direct transition from the valence band to conduction band, giving rise to a very intense absorption. Similarly, the exciton can recombine together to form a very sharp emission also. And another important aspect is the defect tolerance of this material. That is also very, very important for the optoelectronic device application. If you compare with the traditional semiconducting materials like cadmium selenide or gallium arsenide, you can see the traps formed in these materials are actually within the band gap. So that is a very dangerous situation, because the trap will act as a this trap will trap can actually absorb the charge carrier units and charge carrier holes and electrons, and that because of that trapping, the efficiency, overall efficiency of this material can come down drastically if the traps are formed in this material. And these materials are very prone for formation of the traps also. But in the case of perovskite, halide perovskite material, actually the possibility of the trap formation is relatively less. And even though if it is a network in this material, as I said, it actually acts as an express medium or express way for this charge carrier charge carriers to travel along the material structure. But though these materials are having very, very unique properties and unique optoelectronic properties, there are two major challenges associated with this material. One is the toxicity, and second one is the instability against the moisture and the heat and light. The toxicity is mainly because of the presence of lead, because we are mostly talking about the lead-based halide perovskite that is showing the best efficiency. Whatever I showed in the previous slides, the best efficiency like 25% and above, it is actually shown by a lead iodide, and the presence of the lead or the lead is present in the form of water-soluble forms. And when you discard this material after the usage, and these water-soluble lead ions will reach the environment and it can enter into the food chain, and that will have serious consequence of the in the environment as well as the health of living beings in the on Earth. So it is important to get rid of lead from the halide perovskite materials as well as devices. And the second issue is associated with the stability of this material. Many of these perovskite material shows instability against moisture, heat, and light. This is mainly due to the steric effect in the perovskite structure. This 3D structure is actually highly steric, and because of that presence of steric effect, actually it will try to dissociate into a more stable form. Actually, the more stable form is basically the precursor form. So this material, especially in the form of especially in the presence of moisture, it may convert it into the precursor state. So that is another important challenge in this area, and I will talk about these challenges, that is the toxicity of the material and how people are trying to do research to make a new material, especially lead-free perovskite material. I will show some slides in the later slides, and how people are trying to address the instability issue in this material. Before going to those details, actually, you can make this perovskite material in different forms. So we were mostly discussing about the 3D, and that is having the AMX3 or ABX3 structure. But if you have different applications, you can actually make them in 2D, 1D, or zero-dimensional structures. And it actually decided by the nature of the organic unit you are using. If you are using a small organic component like methyl ammonium or formamidinium, you will be getting 3D perovskite. But if you are using slightly bigger cations like ethyl, propyl, or butyl, or bigger aromatic cations which are able to self-assemble, they can actually form layered perovskite like 2D perovskite, or one-dimensional perovskite like this, or 0D perovskite. And depending on the structure and property, you can have a variety of application for this material. In addition to solar cell that we already mentioned in the previous slide, in addition to solar cell, you can have highly efficient light emitting diodes out of this material. You can make micro or nano lasers, and there are several groups involved in this area making lasers, which have a lot of application in many areas. And you can make non-volatile memory devices, detectors like X-ray detectors, transistors, You can use it for lithium-ion batteries as electrodes, and it can be used for as sensors and piezo electric generators or thermoelectric generators or ferroelectric generators. So there are variety of applications, and you can, depending on your application, you can have or you can make different structures like this, like simple 3D structures or 2D structures or 1D or zero-dimensional structures. And by converting the 3D structures or by making the 2D, 1D or 0D structures, you can actually improve the stability of this material, because the steric issue is mainly played in the 3D structure. So once you go to the low dimensional perovskites, the structure will be more and more stable. And in addition to this class of material, people make a large number of halide perovskite nanocrystals also, mainly for the light emitting applications. And this is also a very important class of, or very important area of this topic, in this topic. And as I mentioned earlier, you can actually tune the optical and electronic properties of this material very easily, and particularly in the nanocrystal form. When you convert the chloride in the structure, for example, this is the chloride, and you are getting an absorption close to 400 nanometer and emission also close to 400 nanometer. When you replace chloride with the bromide, the emission will slowly move from blue color to green color, very bright green color. And again, you replace bromide with iodide slowly, then you can move from bright green to bright yellow, then orange, red, and deep red. And this material show very high photoluminescence quantum yield. Normally you can get 90% and above easily, and in some cases 99% and even 100% are possible. And these emission colors can be finely tuned, as I mentioned here, and the color purity is very, very high, because the full width at half maximum is very, very narrow, like 12 to 42 nanometer in most of the cases. Because of the narrow full width at half maximum, you can have the, or you can have a very, very high color purity. So these are very unique properties of this material. And my research group also doing a lot of research in this area, especially perovskite based nanocrystals. And we are mostly using two methods for the synthesis of this material. One is the reprecipitation method, and second one is the hot injection method. Both are in fact very easy, and you can, in the first method, you can dissolve all the precursors in a medium like DMF, including the capping ligands. So this is one of the important thing in the perovskite nanocrystal, that is the presence of capping ligands. In the 3D perovskite or the bulk perovskite, you don't need any capping ligand because it is there, and you don't need any quantum confinement. In order to bring quantum confinement as well as to enhance the stability, we actually use this ligands in nanocrystals, and you can mix all the precursors, including the capping ligands, in a solvent like a DMF, and stir it for a few minutes, and finally you add some anti-solvent like hexane or acetone, and you can get precipitate. And this is the precipitation of the perovskite nanocrystal. You can centrifuge it and use it for the for any applications or studies. So this is one method, and second one is a hot injection. This is slightly different. You can dissolve the one set of precursors, especially the precursor containing the B metal cation and the halide ion precursors, and dissolve this material, these precursors by heating, and you can quickly inject the once it is dissolved, you can quickly inject the A precursor to the reaction medium, and you will get beautiful perovskite nanocrystals with a bright emission. And other methods used for the synthesis includes ultrasonication, mechanosynthesis, reverse emulsification, etc. But in our group, we are mostly using the reprecipitation and hot injection method. And with this method, we were able to make a variety of structures like cubic, or you can say square-shaped structures, and hexagon-shaped one, and nano-rod-shaped and nano-flake-like structures. And we were mostly using methyl ammonium or formamidinium as the organic cation. And our materials are very stable. Even if you dip it in water, you can see it can survive for several minutes. But in the case of bulk perovskite, it can immediately decompose because, as I mentioned earlier, in presence of moisture, it decomposes into the starting material. But that happens only in the case of normal perovskite or the bulk perovskite. But if you incorporate capping ligands like this, you can have much higher stability. Not only stability, you can process this material in a variety of solvent like shown like hexane, toluene, THF, dioxane, chloroform, etc. Except highly polar solvents like DMF and DMS. So in highly polar solvent, it decomposes into the precursor material. So it cannot be used. And another important aspect of the perovskite nanocrystal form is that it can form very smooth films like this, and it is very essential for the device application. On the other hand, the bulk material normally form very rough films. And we did extensive photophysical studies with this material in the normal films as well as self-assembled film. This is a normal drop clustered tape grid. You can see isolated perovskite nanocrystals. But if you add a few more drops into the grid or in a surface, you can actually have more number of perovskite nanocrystals in the same area, and that actually start interacting with each other. And that can be reflected in the emission spectrum. Essentially, the absorption spectrum won't change whether in the solution or in the film state. You can have a comparable absorption spectrum. But in the case of emission, you can see a slight redshift in the emission spectrum because basically because of the excitation energy migration because of closely associated perovskite nanocrystals. And we did study the electron transfer properties of this material first in the solution state. When we added a very strong electron acceptor like a C60 into the perovskite solution, we were able to see a significant quenching in the emission. This is actually highly emissive, but on addition of the C60, it is a electron acceptor. So the perovskite nanocrystals must be acting as an electron donor, and you can see a significant quenching of this material in presence of C60. But interestingly, the result in the solution state and the film state is hugely different. In the solution state, we actually see the quenching in the emission that you can see here. You can see initially a very high amount of photons are coming from the system, but on increasing the amount of the C60, it undergoes quenching. Number of photons coming from the material is very less, but at the same time, there is no change in the lifetime. So that indicates that if one C60 is interacting with the one perovskite nanocrystal, it completely quenches the fluorescence coming from the nanocrystal. So it is no longer emitting. But whatever is emitting or the remaining in the solution without interacting C60, it is emitting as usual. And that is why we are getting no change in the fluorescence lifetime. So that is basically indicating a static quenching in this material in the solution state. But interestingly, in the film state, you can see both quenching in the fluorescence as well as in the quenching in the lifetime. Because in this film state, they are actually self-assembled to form a continuous network of perovskite nanocrystal. And we actually added very small amount of C60 in the film state compared to the solution state. Because even if you have one C60 in one part of the film, the exciton generated in one area of the film can reach the C60 molecule and it can undergo quenching. So that is why it shows a very significant quenching in the presence of, even in the presence of a small quantity of C60. And the excitation energy migration in this material is actually reflected in the long lifetime of this material. So it is actually summarized here. Initially, the perovskite nanocrystals emit without any problem, and normally it is having a very high quantum yield. In the presence of the C60 molecule, actually it transfers the excited electron to the C60 and quenching happens. But in the presence of film state, that is shown here, which is a continuous network, and excitation energy migration, either the exciton or even the charge carriers, separated charge carriers can move very efficiently from one state to another, one point to another, and it undergoes quenching. So that is why we see a significant quenching in this case. And we also did a detailed analysis of the role of excitation intensity of the laser, how it is affecting the generation and the recombination of the excitons as well as the charge carriers. We found that with the increase in the excitation light intensity, there is a significant decrease in the lifetime, but at the same time, there is an increase in the photon counts. So that is basically due to the increase in the radiative recombination. When you increase the laser fluence from 0.0175 to 35 microjoule, there is a significant increase in the number of excitons formed or the number of charge carriers formed. And with a high rate of or high quantity of the charge carriers, the rate of recombination also increases. That is why you are getting a decrease in the fluorescence lifetime. At the same time, there is an increase in the photon counts. And we were able to harvest these excited electrons by doping with the C60, and this harvesting is more efficient when the film was excited with a weak laser fluence, because at that time the excitation energy migration is highly efficient because the film is assisting the migration of the exciton, so the harvesting is more efficient. But at the higher fluence, the recombination become very faster, so only a very small fraction of the excited electron is remaining for transfer to C60. And we utilized this capability or the property of this material, that is the electron transfer property of this material, to use it as a sensor platform for the detection of explosive vapors, particularly the trinitrophenol. And this material can show selective detection of trinitrophenol compared to dinitrotoluene or trinitrotoluene, because it is because of the hydrogen bonding interaction between the perovskite nanocrystal as well as the phenol group in the explosive, and we utilized it for the detection of this material. And we also studied the light harvesting anti-properties of this material, and it is very useful for the development of artificial light harvesting devices or the light harvesting systems. And we basically used three dyes. Two belongs to the rhodamine, rhodamine B and rhodamine 101. And we used a Nile red also to see whether the binding interaction is important or not, because in the first case, there is only one binding site is present, and this can bind effectively with the perovskite nanocrystal, because the electrostatic interaction is very much possible with the perovskite nanocrystal surface. And the second molecule is having two binding sites, one is having here and one is here. And because of the increase in the number of binding sites, we actually found a super quenching phenomenon in the case of rhodamine 101, and that is reflected in this Sternböhmer plot. Here the efficiency is relatively low, 50% quenching efficiency. In the case of the second rhodamine dye, it is 91% efficiency. And in order to really know whether it is the effect of the binding group, we took a equally good energy acceptor like a Nile red and doped the solution with Nile red, and we found no quenching in this case because it's a neutral dye. There is no binding site available, and because of that, there is no energy transfer was possible from this material. And we used this material as an energy acceptor also. As I mentioned in the beginning, it's a versatile material. It can be used for several purposes. So earlier we used it as a electron donor, and later we used it as an energy donor. Now we try to use it as an energy acceptor. For that, we selected polyfluorine as the energy donor, and this mixed halide perovskite nanocrystal as the energy acceptor. This is the absorption and emission spectrum of the polyfluorine. It is giving a beautiful blue emission, and this is the absorption and emission spectrum of the selected perovskite nanocrystal. It is yellow emitting, and this is blue emitting. If you mix a blue emitting donor, energy donor, with a yellow emitting energy acceptor, normally you will end up with a white light emission. And we are also able to see very beautiful white light emission by combining the blue emitting energy donor and the yellow emitting energy acceptor. And unfortunately, this white emission was not so stable, because after some time, like 5 to 20 hours, we can color shifting from blue red emitting to blue emitting. This is because of the presence of the mixed halogen in this material. Because if you have a combination of halide in the perovskite structure, normally the weakest bond will start breaking because of the steric effect. Here in the case, the weakest one is the iodide, and this lead iodide bond breaks, and only the lead bromide bond will be possible, and iodide will be escaped from the medium through sublimation. And that because of that, we are getting predominantly the emission coming from the polyfluorine. That is why the white emission converted into blue emission. But we what we did, that we used this polyfluorine in the gel state, and gel is actually a very effective medium and a very confined medium. In the gel medium, we found that it can arrest the halide ion migration. Actually, this halide ion migration is one of the issue related to the perovskite material, especially in the for the tuning of the emission. Because though we can say that it is easy to tune, in reality you cannot get all colors because of the this migration of the halide ion. So we stopped this halide ion migration in the presence of the polyfluorine gel network, and we were able to get very stable and very bright white emission this material. And next, we tried to develop a visibly opaque and NIR transmitting material with this perovskite nanocrystal. For that, we selected a formamidinium-based perovskite nanocrystal. Why we try to make visibly opaque and NIR transmitting material? Because these materials, this kind of NIR transmitting visibly opaque material, having application in security and NIR photography, as well as in night vision cameras. And this is the material we used. And for that purpose, actually, you need a very strong absorption till 740 nanometer. But there should be a significant increase in the transmittance after 740 nanometer. So it needs to cover the visible region. The absorption should cover the entire visible region up to 740 nanometer, and it has to you should have a very good transmittance above 740 nanometer. And in order to get a very good absorbance, we try to remove some of the capping ligand from these nanoparticles. And once you remove the nanoparticles, this capping ligand, actually these capping ligands are very labile and easy to remove. You can actually allow the growth of this nanocrystal, and once you allow the growth of the nanocrystal, you can actually improve the absorbance in the longer wavelength. That is why you can see the compared to the zero washed perovskite nanocrystal, you can see increase in the absorbance when you wash it one time or two times. Similarly, you can get a corresponding change in the transmittance spectra also. And it is the process happening during washing is represented here. During washing, the fusion happens, and you are getting an improved absorbance in the longer wavelength region. But it was not enough, because you can still have more than 2% emission absorbance in the 650 to 740 nanometer. In order to make a visibly opaque and NIR transmitting material, you in fact having a lower than 2% absorbance in transmittance in the visible region. For that, actually, we incorporated a very simple squarine dye in this molecule, in this material, and we were able to get a very good transmittance above 740 nanometer. At the same time, very good absorbance in the visible region, and this absorbance is very, very high. Because of that, the transmittance was below 2%. That is very much ideal for making a NIR filter. And with that material, we proved this is suitable for the security application, as well as for the NIR photography, as well as the night vision camera application. And we recently published this paper in this year in Advanced Optical Materials. And we also used this for some device application with the help of my collaborators in IIST particularly for the memory device application. I am not going to the details of this work. We were able to show that the switching behavior of this material can be controlled by changing the chemical structure, especially by doping this material with a chloride ion. And we were able to get very high performance air stable non-volatile memory devices, mainly fabricated through processing technique at ambient conditions. And next step, we are trying to explore these perovskites for neuromorphic computing application. And for that, we have a collaborator in Poland, and the DST approved this project. And we will be exploring our material for the neuromorphic computing application. This is an upcoming area. Here we use the devices as similar to the neurons in the human brain, and that can be used for the computing application. And I'm not an expert in that area. That is why I collaborated with a person expert in Poland, and we will be exploring this area soon. And coming back to the stability issue, so the perovskite nanocrystal structure, the stability is not an issue. It's very, very highly stable. But at the same time, because of the presence of the capping ligands, the conductivity property of this material is like 1 or 2 order less than the conventional 3D perovskite. So in order to get performance equal to 3D perovskite, but at the same time getting a long-term stability, actually recently people reported 2 classes of perovskite. These are basically layered perovskite called Rudelston Popper perovskite and Dio Jacobson perovskite. The difference between these 2 perovskite that here you have 1 binding site for the organic unit. Actually, this organic unit is a bulky organic cation, and it is having only 1 binding site for the first class, and it is having a 2 binding unit in the second class. And especially in the second class, it is found to be very promising, and it can give about 20% efficiency according to very recent reports. So this is a development, especially in the part of the stability part. You can either make the material in the nanocrystal form and get a very interesting properties, and it can be used for most of the application, but not so suitable for the solar cell application. If you really looking for solar cell application with the long-term stability, you can have these 2 classes of material and get a relative reasonably good efficiency. But still the presence of lead is a problem. So people are looking at lead-free perovskite material. So these are the possible replacement. One is tin, and another one is germanium, and both this germanium and tin belongs to the same group. So it is isoelectronic, so it have similar properties that of lead in many aspects. And other possibilities like antimony, bismuth, indium, and silver as the cation, and you can use again chloride, bromide, iodide as the halide component, and rubidium or cesium or the methyl ammonium or formamidinium as the other cation. And extensive research is happening in this area. According to some reports, especially came in this year, people found that this tin-based perovskite can give almost up to 13.24% efficiency. But tin again is not a really non-toxic material. Of course, you can say that compared to lead, tin is less toxic, but we need to look at better material or better metal cation, which is very, very or relatively non-toxic. So these are the possibilities like bismuth and germanium. And my group is especially interested in the bismuth-based structures. And very recently, we reported some of the bismuth-based material and use of this material for some optoelectronic device applications. And this is the first one we reported, that is a methyl ammonium bismuth iodide. It is a it's a zero-dimensional perovskite having 2 octahedras are having a phase-shared structure. And since the methyl ammonium cations are freely available, they showed enhanced ion transport. And since it is having low dimensionality, the octahedral structures are approachable from any side. And because of that, it is having very large electroactive surface area. And we were able to make very nice film without pinholes. And we used this material in the capacitor device architecture, and we were able to get a relatively good performance and very good stability also. Even after 10,000 cycles, we were getting close to 85% efficiency. And the capacitance of this material is mainly due to the movement of the methyl ammonium and iodide ions from the electrolyte to the electrode and vice versa. And this is the first lead-free perovskite-based capacitor reported in literature. And later we try to use bigger organic cations and see what is happening in this kind of materials. And this is the second one we reported. That is, in this case, we used a bigger cation like propane diammonium cation with the 2 binding site. And this is forming octahedral structures with edge sharing, and it is actually forming a quantum well structure. And this inorganic component actually having the quantum well structure, and the inorganic, it acts as the quantum well, and the organic component as the energy barrier. And because of this unique structure of this material, you can see the C-axis of this material is actually connected by the means not really connected, only two octahedral structures are connected. The other one is not connected, but it is in the very close proximity without the barrier of organic cations. And because of this arrangement, you can have very interesting property. And before going to that property, I would like to explain that this material is showing a split conduction band like this. It is shown here, and because of the split conduction band, we were able to get a dual emission. One is from this conduction, and the second one is from this. But at the same time, you can see the density functional theory calculation show that there is no involvement of the organic cation into the electronic structure of this material. And in the subsequent work, we were trying to incorporate or trying to make it involved in the electronic properties of the material that I will explain in the coming slide. And we used this material for the photo detector application. As I mentioned, this along the C-axis, there is no hindrance of the organic cation in this material. And because of that, it shows very good conductivity, electrical conductivity, and it showed very high sensitivity towards light. And with because of that, we were able to get relatively good photoconductor devices with this material. And in the next work, we incorporated a polarizable organic cation to see how it is affecting the material properties. Because earlier in the first case, we incorporated a very small organic cation, that is a methyl ammonium cation. And in the second case, we increased the structure. But at the in that case, both quantum confinement and dielectric confinement was present. And these are the two major issues of this class of material. One is the quantum confinement, and the second one is the dielectric confinement. And dielectric confinement is nothing but the difference in the dielectric property of the organic and inorganic material. And because of the huge difference between these two dielectric polarizability of this material, actually that hinder the free flow of the charge carriers in this material. So in order to reduce the dielectric confinement, you need to use high dielectric constant material, and the high dielectric constant material should show better polarizability. So we selected a organic material which is capable to show polarizability. That is why we selected benzyl ammonium cation, and as we expected, it showed a beautiful polarization. And because of that, we were able to get a reasonable photoconductivity in this material. In addition to that, actually, the stacking of the this benzene cation is actually affecting the stacking of the inorganic component. Normally, the structure of the material or the stacking of the material is controlled by the organization of the inorganic material. But in this case, it is actually controlled by the organic part. That is a unique observation. And because of these reasons, especially the polarizability of the organic cation, the charge transport in this material was much easier, and because of that it showed very good photoconductivity, especially when compared with the traditional methyl ammonium bismuth iodide. So the lower one is the methyl ammonium bismuth iodide, and the second one is our material, the BBI material, and it showed very good photoconductivity because of this unique polarizability ability, and because of that it shows higher dielectric constant and lower dielectric confinement in this material. And next we moved to another one, a bigger cation we used.
Vijay, 3 minutes.
Here, Joshi?
3 minutes.
Okay. So we used a naphthalimide methyl ammonium iodide in this material. So in addition to the ability to polarize, and it can actually stack along the pi orbitals, and that actually can provide some support for the charge carrier mobility. And because of that, we were able to get a very long-lived charge carriers and anisotropic photoconductivity in this material. And this basically forming a type 2A band alignment in this material. And this band alignment is very unique. I will show that band alignment in the next slide. And because of that particular type 2A band alignment in this structure, we were able to get a very good photoconductivity and anisotropic, which is anisotropic. So this is the band alignment. Theoretically, 4 types of band alignment is possible in a layered perovskite structure. One is type 1A, 1B, 2A, and 2B. And in the case of 1A, both the conduction band and the valence band will be decided by the organic material. And in the 1B structure, both conduction band and valence band will be decided by the inorganic component. In the 2A alignment, the conduction band will be decided by the organic. On the other hand, the valence band will be decided by the inorganic component. And it is just opposite in the case of type 2B alignment. And in a, normally, we are using electronically inactive organic cations in a perovskite structure, and we normally end up with a type 1B band alignment. That is, both the conduction band minimum and the valence band minimum will be provided by the these inorganic materials. And we were actually trying to incorporate the electronically active organic cations to this material, so it can contribute to the band alignment. That is why we are looking at these type 2A structures. That is what I showed in the previous slide. And we made another very interesting molecule by using this concept, and we were able to incorporate a electronically active organic component into the structure. And because of that, we were able to get a band gap below 1.8. It is very, very difficult in bismuth-based structures. Normally, you will end up with 2 band gap 2 and above. But in this case, we were able to get 1.8, and that is mainly due to this approach. We were able to incorporate stacking organic components which are stackable, and it is giving means contributing to the electronic structure of electronic properties of this material. So in summary, the perovskite solar cell made huge strides in efficiency, and you can see more than 25% efficiency in the last few years, and that made them today's most promising photovoltaic technology. Among the emerging photovoltaic technology, you can say it is the most promising one, and further efficiency can be expected from this material through the engineering, the material side, as well as in the device architectures. And the second point is that other equally important optoelectronic application of this material are light emitting diodes, photodetectors, lasers, memory and artificial synapses, transistors, sensors, and other electronic devices. These are also equally important, just like solar cell. And my own group has done a lot of research in this area, and we mostly were looking at the photophysical properties of the perovskite material, especially the perovskite nanocrystals and the bismuth-based systems. And particularly in the self-assembled state, we studied the electron transfer, energy transfer, exciton or charge carrier migration, and we developed the NIR filters and memory devices, and we will be looking at the neuromorphic computing application of this material in near future. And we designed and synthesized several lead-free perovskite, which are low-dimensional materials, and they showed a very promising optoelectronic properties, especially which can be tuned by the selection of the organic cations. That is the aspect we are mainly looking at by selecting the suitable organic cations which can self-assemble and which can contribute electronically to the structure. We were able to tune the properties significantly, and we used this material for capacitor and photodetector applications. And finally, I thank my students, and the most of the work I showed are the contributions of Mr. Chinnadure and John Ford, and my collaborators, Dr. Biju, Professor Biju for Hokkaido University for the laser studies, and Professor Sudeep Chakrabarti, IIT Indore for the DFT analysis, Professor Akinori Saeki, Osaka University, Japan for the photoconductivity analysis, and Dr. Jinesh, IIST Trivandrum for the memory device application, and Dr. Agi for the capacitor devices. And I have active collaboration with Professor Konrad Silowski, Poland for the neuromorphic computing application, and Professor Sergei Makarov, ITMO University, Russia for the micro and nano laser application of this material. And I thank the funding agencies, especially my parent agency, CSIR and CSIR-NIIST, and the DST through various funding like Ramanujan Fellowship, DST SERI, DST RFPR, DST CRG funding, and the Poland project. And finally, I thank all of you for your kind attention, and I am very happy to answer if you have some questions. So Joshi, I'm done.
Thank you, Vijay. Thank you, Vijay. I don't see any questions in the chat box, and I have shared your email address in the chat box. So due to the interest of time, we will go ahead. And
thank you, Joshi.
I request all the participants to post your if there is any questions to Vijay directly at cvk121@gmail.com. And I should comment on this material that it is a very important material and a new material. So probably the students who are doing PG and all is going to hear about this material a lot in the coming years. So thank you very much, Vijay, for introducing these wonderful materials to this community, and all the best for your research. And thank you. With this, we will move to the next lecture by Professor Dr. Ajay Venugopal. So, Ajay, you can share your slide. He is an associate professor in IISER Thiruvananthapuram, and he did his PhD from University of Münster, Germany, and then did a postdoctoral research at Oslo, Sintef Materials and Chemistry Department, Oslo, Norway. And he also is a recipient of Kerala Young Scientist Award by KCST, and then Inspire Faculty Fellowship, Humboldt Research Fellowship, and the NRW International Doctor Fellowship. With this short introduction, I welcome Dr. Ajay for his presentation. I will let you know when you complete 50 minutes, and then we can conclude it in 1 hour. Thank you.
Yeah, thank you, Dr. Joshi, for the very kind introduction. And at the very outset, I have started my timer, so I will finish it within 50 minutes. I would like to thank the organizing committee of the FCBS. My special respects to Professor Rao, and my homages to Professor M.V. George. And also, I would like to thank Dr. Suresh Das for extending this invitation to make a presentation here in this stage online platform. And also my thanks to my colleague Dr. Reggie Varghese, and also Dr. Joshi Joseph for organizing this and inviting me here. So in the next 15 minutes, what I will try to do is to take you through a journey of an area in main group chemistry. I had initially titled this as a contemporary main group chemistry when I started preparing the lecture, and then I thought there were a lot of things which I had to tell, and everything got jumbled. And I thought of just focusing on Lewis acids today. Okay, so I will be discussing on the Lewis acids of the P block element, and I will start with very fundamental things, starting from the school chemistry, and finally take you to the research what we are doing in our lab. And I am aware, I have been told that there is a mix. The audience has a mixture of college students, teachers, and also some postgraduate and also some PhD students. So I hope to reach you all. And if you have any difficulties, you can always get back to me. Okay, let me begin my talk with the very fundamental concept of Lewis theory, where it was G.N. Lewis, one of the greatest chemists of our times. There are lots of nice biographies on him if you want to go through, especially in Journal of Chemical Education, which appeared between 1950 and the 1990s. Students have to read his biography and the style which he dealt with his students. And he's one of the considered to be very wise persons among the scientific community. So the Lewis acid-base theory actually tells that an electron pair acceptor is a Lewis acid, which is basically an electron deficient species. Let me switch on my pointer. Okay, and the one which donates the electron is a Lewis base. And the standard example which you see in most of the textbooks is the ammonia binding to BF3 or any other trivalent boron compound. So this was a theory which started in the early 1900s, and now this has taken a new shape and it has a lot of implication in catalysis. And this is what I will take you through in the next 45 to 50 minutes. So this is the periodic table, and mostly the S and the P block are considered as the main group elements, or traditionally most of the time the P block ones are the ones which are considered as main group elements. And my friend Vijay Kumar already took you through some of these heavy elements like bismuth, antimony, and tin. So I will also be touching upon it in a short span of time. So these Lewis acids are very well known in organic chemistry. Most of them are, as you see here in the slide, are halide salts of P block elements. The most important ones are the boron compounds as well as the aluminum compound. You are aware that aluminum chloride is an important Lewis acid finding application in alkylation reaction, Friedel-Crafts reaction. And of course, over the period of years, there are several other halides of these P block elements which have found various types of Lewis acid application. And of course, SBF5 has been used by George Olah and co-workers to actually make the superacid by treating it with HF. Okay, and of course, the heaviest and safest element in the periodic table, which is bismuth. The salts of bismuth are also used in many of organic transformations as Lewis acids, and it's a very well used, but there is very limited knowledge of understanding what is the actual role of these elements in catalysis. So let me now browse through most of the Lewis acids of most of the elements. We will start with the simplest one, the smallest element, boron. And most of the textbook give this concept of the halides of borons. And it is many a times it is presented this way, that BF3 is less Lewis acidic than BCl3, which is less Lewis acidic than BBr3. And this basically, the low Lewis acidity at BF3 is explained in terms of electron donation from the fluorine atom, which has an extra lone pair, and it gives back to the empty p orbital at boron. There are lots of controversies regarding this. Textbooks give these type of interpretation. Still, theoreticians are coming up with different theories, and this is still not even up to date. This is not the best definition and best argument known. But worldwide, this is one of the accepted fact. So what normally happens is, if you have a boron halogen bond, if you have a polar bond, this actually results in an empty p orbital, and the extent of polarizability of your boron halogen bond is what is a measure of Lewis acidity. But these halides are sometimes quite tough to use. For example, BF3 is a gas, okay, so, and BCl3 also so as. So the problem is now, can you have some compounds which can be handled in a laboratory and still exhibit similar or even more Lewis acidity? So this is one of the compounds where chemists actually replace these halogens and put organic groups. Okay, so initially they put aryl groups, which was not sufficiently Lewis acidic. Then they started putting electron withdrawing groups. So fluorine, if you put, so you have a perfluorinated phenyl group, and this is one of the most Lewis acidic boron compound. Okay, and you should also note that this compound was actually prepared in 1960s, which was a purely because of a laboratory curiosity, and it only found application after 30 years, where this Lewis acid was used to abstract a methyl group from zirconium center to make a cationic zirconium compound. So as you all know, that from, if you have studied organometallic chemistry, that group 4 compounds have been very well explored in olefin polymerization. So these type of titanium, hafnium, zirconium compounds find extensive use in olefin polymerization, the most famous being the Ziegler-Natta catalysis. So 30 years later, it has found application. That means there are many compounds in store which have not been properly explored. And many a times, inorganic chemistry, especially the chemistry of the P block, is a boring subject in a classroom. But the main reason is the most of the chemistry which has been discussed is all aqueous chemistry, and one tends to memorize few things. But the contemporary main group chemistry, which has happened from 2000, it is very interesting, and your main group chemistry becomes more interesting than actually the transition metal chemistry. And this is what I would like to convince in the next few minutes. Okay, so once you have a boron compound which is Lewis acidic, it can be actually taken along with a Lewis base, which is a phosphine. Okay, and if you take this, and you can actually activate hydrogen. Okay, activation of hydrogen is mainly known with Wilkinson's catalyst. This is something which many of you might have seen in your textbooks. But now we have the concept of a metal-free catalysis, a hydrogen cleavage. Okay, and this has been successfully used in the reduction of organic molecules and also derivatization of carbon dioxide into value-added product. So as you see, this chemistry is all very new and it's all very interesting. And this process of hydrogen uptake and release has been shown to be a reversible process. Okay, and over the period of years, scientists have been, chemists have been attracted towards preparing various boron compounds with varying Lewis acidity, and this is one of the examples which shows that you can actually increase or decrease the Lewis acidity at boron by actually choosing the right groups bound to the boron center. And generally it is known that the increasing fluorine atoms on the aryls tend to increase the Lewis acidity. You see that in most of the cases here. So now one tend to ask, see, for example, if you take Bronsted acidity, this is very easy. Everybody can make a measure. So you have sulfuric acid, hydrochloric acid, nitric acid, acetic acid, many such protic acids. You have a common scale to actually put them in the order of their acidity, which is the pH scale. But this is not the case in with Lewis acids, because each element has its own chemical nature, and this becomes difficult. Its position in the periodic table is all different, and hence it may have different electronegativity, different properties. So it becomes very difficult to compare these elements. It's almost becomes like comparing apples and oranges. But in the case of Bronsted acidity, H+ is the only scale which you take, which is pH. So but still, people have tried to make a scale for this Lewis acidity. And one of the methods is actually using treating a Lewis acid with a Lewis base. Okay, so this is a phosphine oxide, and you bind this oxygen to the Lewis acid. And then it forms a Lewis acid base pair. This is just like the ammonia BF3 pair, which I told in the earlier slides. Okay, and then what you do is through NMR spectroscopy, you try to measure the extent of deshielding of this phosphorus, because now the phosphorus atoms becomes more and more deficient of electrons, so the phosphorus signal should become deshielded. And this is what is there in this table, where you can have various types of boron Lewis acids and you can actually scale them. And as you notice that your the boron triiodide is the most Lewis acidic compound. So this can be actually scaled into something called acceptor number, okay, where you can use a small formula. I don't want to get into that, but essentially your phosphorus chemical shifts tells you the Lewis acidity. So you can also have various organoderivatives, and you see that the perfluorinated borane has significantly high Lewis acidity. Okay, and this is something very close to the halides, but still you can't beat the halides. Okay, so if you cannot beat the halides and you are still the Lewis acidity is below them, what can you do? One of the things which you can do is actually remove one of the groups at boron and create a positive charge on that. And this is what people tried. So they started with a trivalent boron compound and actually ripped off one of the fluorines from here to make a cation. So this becomes now significantly Lewis acidic. And you also see that the anion which is there, this plays a crucial role, because if you have something like a PF6 or SBF6, they will go and directly bind to the boron center. So you need to have a non-coordinating or a very weakly coordinating anion to actually create such cationic species. So these type of compounds can now activate carbon dioxide, and they can cleave the carbon dioxide. And as you see here, in this reactivity, you get a mixture of compound, and you can rip off the oxygen from the carbon dioxide and get the oxoborane compound. So the stabilizing factor is so you have a p-pi bonding here through the boron carbon, which is actually stabilizing this cation. Okay, it's a true 2-coordinate boron compound. So people started looking at these things, and if you go down the group, next to boron is your aluminium, and if you try to do the same test with the triethyl phosphine oxide, make it a Lewis base, you see that aluminum chloride also exhibits significant amount of Lewis acidity. But then if you try to create a cationic boron center, it shoots up from 84 to 117. So you now get a tool to actually enhance your Lewis acidity by creating a charge on these p block elements. Okay, so this is one way, and the other way is, as you go down the group, your aluminum now has a larger ionic radii, and this becomes very difficult to handle because aluminum can go up to a coordination number of 6. And unlike boron, which goes to maximum 4, and this makes the whole thing very complicated. And but still, people have been trying to replace aluminum chloride by simple molecular compounds. This is actually this compound has alkoxo groups. Okay, simple. You deprotonate an alcohol, you get an alkoxide, and the advantage of this compound is all the protons of this tertiary butoxide have been fluorinated. So it's a perfluorinated tertiary butoxide, and you have 3 of these perfluorinated tertiary butoxide bound to aluminium. Now, this is so Lewis acidic that it can interact even with weak nucleophiles like fluorobenzene. Fluorobenzene is one of the weakest nucleophiles among the solvents used, but it can even interact with it. And you see that this compound, which is mentioned here, okay, this is so Lewis acidic, it can actually abstract a fluoride from SBF6. Okay, SBF5 is one of the strongest Lewis acids known, and now it can take up a fluorine to become fluoride to become SBF6 minus. So taking off this fluoride is not an easy job. So if you can abstract one of the fluorides, so that means that you have achieved a super Lewis acid. This was actually reported in 2008, and as you see, the chemistry is so new, and most of the main group chemistry which is happening, it has actually changed the arena and changed the way people look at p block elements. Okay, so there is one more scale for Lewis acidity, which is actually the fluoride ion affinity. I actually showed you in the last slide that you can take if you can abstract a fluoride from SBF6, you can consider that as a super Lewis acid. So actually, Crossing and co-workers have come up with this theoretical investigation. It's just a thermodynamic calculation. If you have an acid and react it, if you bring a fluoride near the acid, the energy which is liberated once the acid base complex is formed is actually a measure of Lewis acidity. So in this, you see that your SBF5 has a fluoride ion affinity of 490 kilojoule per mole. Okay, and whatever which is above SBF5 is considered to be a super Lewis acid, because SBF5 is one of the most strongest Lewis acid known. And you see that all the boron Lewis acids come very, very low compared to SBF5. At the same time, you also notice that most of these Lewis acids which are present here have these fluorine derivatives, which is actually drawing the electron density from the p block element center, making them highly Lewis acidic. Okay, and you have various values. You also see that your aluminum chloride, which is here, it is not as Lewis acidic as SBF5, but still strong enough to perform many reactions. Okay, and as you go low, BF3, one of the weakest among the boron halides, has a fluoride ion affinity of 338 kilojoule per mole. Okay, so we were talking about group 13 Lewis acids. We were discussing about this, and let us now move to group 14. Carbocation chemistry is very well known. Okay, this is very old, and it happened in the late 1800s, where there were many people starting from Friedel Crafts and many people who contributed for this carbocation chemistry. And significantly in the 1900s, George Olah contributed quite a lot for this in this area of carbocation chemistry. But then it is very well known that these carbocations are stabilized, resonance stabilized by the aromatic groups or any other groups which are present here. If you go down the group to silicon, whether a similar sort of a stabilization is there? So it is actually not, because once you go down the group, your pi overlap becomes very ineffective because of the difference in the atomic radii of these elements, for example, silicon and carbon. Okay, so people wanted to actually make a cation of silicon. This is just like a carbocation, a silyl cation. Okay, and this is actually there were early attempt. You see, E.J. Corey, well, Nobel laureate, he tried in 1975. So what he did was he took a trityl. Okay, this is three of the phenyl groups bound to this carbocation, and he had perchlorate as one of the anions and treated this with trialkyl silane. And the aim was to make a silyl cation, and the driving force of this reaction is the formation of a stable CH bond. So it was actually, it's mentioned here that it is a failed attempt because perchlorate strongly binds to the silicon center. Silicon oxygen bond is very strong. It is around 800 kilojoule per mole. And then once you form that, you don't have a cation, but you have a molecular compound. So it took several years. You see, it took 2 decades to actually develop a non-coordinating anion. This is actually a tetraborate anion. So you have 4 groups bound to the boron center. Okay, and with this anion, the same reaction was repeated, and then one could achieve the silyl cation. Okay, so there were several people who contributed for the silyl cation, which is one of the strongest Lewis acid known among the p block elements, because after aluminium, silicon is the second most electropositive element among the p block. Okay, aluminium, people still have not been able to achieve the reactive compound which is more stronger than the silyl cation. So the race is still on. Okay, but nevertheless, silyl cation was achieved. This was Lambert and co-workers who actually prepared this triethyl silyl cation. It's a planar molecule, but then you see that the solvent used in the reaction, toluene, the aromatic ring strongly interacts with the cationic silicon center. Nevertheless, they were able to isolate this. Okay, and we see that the angle here is 114 degrees, the angle at silicon. So it's because of the toluene coordination, it goes low. Okay, and once they increased the sterics from ethyl to isopropyl, okay, they saw that the silicon carbon angle went nearly up to 120, which tells that it is going to the planarity. And this was actually done by Christopher Reid, who was actually competing with Lambert's group. But then Christopher Reid and Lambert, they together came up with this idea. I don't want to get into the depths of this reaction, but then they got a tris-mesetyl silyl cation, which now has a perfect 120 degrees. But then, interestingly, there is no hybridization here. Okay, so your empty p orbital on the silicon center does not take up any back donation, unlike in the case of the boron cation, which we saw earlier, which tells that the back donation from the aryl ring cannot happen to quench the Lewis acidity at silicon. So it took around nearly around 6 to 7 years, or even, for example, 10 years for somebody to find out an application of the silyl cation. It was Ozero who found out that these compounds, these silyl cations, can be used for actually removing removing fluorine from an organic compound and replacing the fluorine with a hydrogen. And this sort of a reaction is called hydrodefluorination reaction. Okay, and so what you essentially do is you have a fluorinated organic compound and you treat it with the silyl cation in presence of the silane, and you remove SiF. The driving force of the reaction is the formation of a strong silicon fluorine bond. Okay, and then you regenerate and the catalysis proceeds. Okay, so that is about silicon. And when people came down the group, they have been still unsuccessful in making strong Lewis acids. The area is still open. People have been working with germanium and germanium, tin, and lead compounds. But as you go down the group, because of your inert pair effect, your +2 oxidation state becomes more and more stable. And once you have only +2 oxidation state, the inherent Lewis acidity is very less. And there you will have a limitation in achieving strong Lewis acidity. And nevertheless, you can now move to the next group of the periodic table, which is the group 15. And then you see that phosphorus has been explored for Lewis acidity. And this is one of the examples where a cationic phosphorus center has been generated, and it is actually stabilized by a carbene ligand. And the main limitation with this type of a compound is the delocalization of the positive charge. So you try to abstract one of the chloride from the phosphorus center to make a cation, but then in the presence of a carbene type of a ligand, it will donate extra electron density, and the positive charge actually goes to the carbon center. So effectively, the compound is very stable, but it will not be reactive. So people have been trying to use other ligands, okay, and so you see that this is a phosphorus dication which has been prepared, but then this tends to become highly unreactive because there is a lot of steric crowding around it, and it becomes complicated to use such type of compound. Okay, so that was about phosphorus 3, but then you can go to the higher oxidation state, which is +5. And so what people have tried to do is start with actually a +3 oxidation state phosphorus compound and treat it with xenon difluoride. And this is very well known from the textbook chemistry, that xenon difluoride is a highly unstable compound and it is a good fluoride source. So now you can oxidize your phosphorus from +3 to +5 and get a higher oxidation state compound. You can now add 2 fluorides to it. Now it becomes a +5 oxidation state. And now what you can do is abstract one of the fluorides to make a cation. Okay, and this cation, which is presented here, it is now tetrahedral. This can do the same work as what can be done with the silyl cation. Okay, so this was one more advancement after the synthesis of the silyl cation. Now one can expect to have phosphorus in the +5 oxidation state to express super Lewis acidity. Similarly, going down the group, one can even think of having other cations. So it was the antimony. Okay, arsenic is quite toxic, and people refrain from doing that chemistry unless there is a valid reason. So antimony is less toxic, relatively less toxic, but still it is toxic. So the idea was SbCl5 is highly Lewis acidic. If you put perfluorinated aryl groups, will it be Lewis acidic? But this was not the case. This is not Lewis acidic. So the next approach was to remove one of the aryl groups and create a cationic charge. Okay, so this compound again shows a lot of Lewis acid behavior, and very surprisingly, this compound is stable in presence of moisture. So this just tells that you can have super Lewis acid, and provided you have these fluorines, so many fluorines around it, it becomes extremely hydrophobic, and you can prevent moisture to kill the Lewis acidity at this P block center. Okay. So when we started our chemistry in our group, we were looking for, because many of these heavy elements are quite toxic. Okay, and as you see here, bismuth, this is one of the heaviest element. Okay, and many a times it exhibits metal-like property. My friend Vijay Kumar already explained lots of interesting chemistry, especially with the perovskites, where he showed 6 coordinate bismuth halides, bismuth iodides. Okay, and you notice that these bismuth atoms can achieve high coordination number. Okay, and now if you actually make a bismuth compound with a low coordination number, this has to be electron deficient, and it can be used as a strong Lewis acid. So this was our idea. But then you also come to know that bismuth is non-toxic. It is actually used in many of the cosmetic industry, and also it is used. There is a medicine called Pepto-Bismols, which is actually used for treating ulcers and various other diseases. Recently, I even saw somewhere like this COVID research is becoming so attractive. Some people are trying to use bismuth compounds to actually make drugs for dealing with the COVID. Okay, and then it is also inexpensive relatively. And the most interesting thing is the ionic radius of lanthanum is the same as bismuth with the coordination number 6. Okay, so in times when rare earth elements are becoming really rare, because China is now controlling the rare earth economy. Although we have lots of rare earths deposits in Kerala, but still one should think of now having looking for alternatives other than rare earth, because I had done my earlier work during my PhD with rare earth elements. Then I thought I should move to some other element. Then I found out that bismuth is actually imitating lanthanum, and then we wanted to see whether we can mimic all the properties of lanthanum using bismuth. Okay, and the other important interesting aspect is you can actually vary the hardness at bismuth. This is the HSAB principle, hard soft acid base principle, which is learned in the undergraduate level. So you can actually tune the hardness at bismuth by actually choosing the right ligands. Okay, and we basically wanted to mimic the lanthanum chemistry, but there was something more to us in the store. Okay, and we set out to make cations of bismuth. And when we looked into the literature, there are lots of reports of cations. Okay, so what people tend to do is take bismuth chloride, treat it with aluminum chloride, which is a strong Lewis acid. So what they do is they try to abstract the chloride from the bismuth center, and then you get a BiCl2+. But then you have a strong interaction with the bismuth center, and the solvent molecule is interacting again with the bismuth center, and this makes the compound less reactive. There has been many efforts in this area. Okay, and this is a similar compound like this, where a chloride has been tried to abstract using aluminum chloride, and also people try to use introduce anionic ligands. So this is an amidinate ligand. It's a monodentate ligand, and it's a bidentate ligand. Sorry, and it's a dianionic ligand. And one of the chloride which is there was tried to be abstracted by this trichloroaluminium or aluminum trichloride. But the point is, these are not truly cationic, and they tend to redistribute, and people have not been able to use in any of the Lewis acid properties. Okay, and what has happened is over a period of time, people have been thinking of making molecular compounds. So this brings us to the concept of these valence electron rule. You know that this concept of valence electron rule, you have 18 electron rule for organometallic compounds. Okay, and you also have 8 electron rule for the p block element. Okay, so these 8 electron compounds are the octet compounds, which are quite stable. Anything less than 8 are electron deficient. For example, your boron compound, 6 electrons, they have 6 valence electrons, and then they tend to be Lewis acids. Okay, but as you go down the group, you can have hypervalency. Okay, and which makes the existence of 10 valence electron compounds possible. Okay, and so these are the various 10 electron species which are known. You can actually count the electrons. So you have 2 of the anionic carbon donor ligand which contribute 2 electrons each, and then you have 2 neutral ligands which contribute 2 electrons again, and then you have a lone pair. Altogether they contribute 10 electrons. Okay, so we have been looking at these 10 valence electron species, and now our idea was, can you remove 2 electrons from this species and make it an 8 valence electron species? Okay, and you can further remove 2 more electrons and make a 6 electron species. So now in principle, this should be really electron deficient as per your octet rule. Okay, but the problem is you cannot stabilize these type of compounds, because they tend to either decompose or disintegrate, redistribute into various type of products. So people have tried using additional donor ligands where they give some electrons, and now you make an 8 electron species here. Okay, and they have looked at this one of the vacant sites which is present in this molecule, and at the same time, to achieve 6 electron compounds, people have used sterically bulky ligands. So what happens is the steric bulk prevents anything to actually attack this MTP orbital, and hence they tend to be very stable. So we actually looked at these compounds, and we found out that you can make similar compounds, something like this. Okay, and actually make see some properties out of this. So we actually made use of this MTP orbital to do some polymerization chemistry. Okay, this was not our this was not so impressive, but it actually told if you can actually control the extent of donation to this orbital. Okay, here you see a 5-membered ring, and here you see a 4-membered ring. Okay, so the thing is, you have the bite angle here. The one with the lower bite angle shows a better reactivity. Okay, so this was the basic concept which we started looking at. And when we looked into the basic coordination chemistry of this, so we saw that the five membered cycles have nearly 90 degrees, and this tends to decrease a bit if you try to create a cation, whereas the 4-membered ring has relatively shorter bite angle. The shorter the bite angle, the stronger is the Lewis acidity. So we actually resorted to making this Lewis acid base adduct, and we found out that we could even isolate these compounds and then show that the 4-membered compound is more Lewis acidic than the 5-membered compound. This is because the nitrogen here gives electron density more effectively as compared to the strained position. Okay, this is not a great Lewis acid, but then you can use this concept of the bite angle, which is a very well known concept in transition metal chemistry, actually used to prepare new transition metal catalysts. Okay, now can be used in main group chemistry also. Okay, we wanted to further explore and see what happens, and we actually, when we took this compound and tried to abstract this chloride, we were at a surprise to get actually a dicationic bismuth. So if you increase the charge, that means you are actually increasing the Lewis acidity. This was a very complicated reaction where we got lots of products, but we could isolate this product. And now this is a 12 valence electron species, which is highly saturated. You can't do much with that. When we actually looked into the literature, many p block element compounds with a +2 charge are known. Okay, so you can see silicon, germanium, and you can see tin compounds with charges known. Okay, and even in the case of group 15 elements, you can see phosphorus, and also you can see tellurium in the group 16. But the problem is most of these compounds have been synthesized and characterized, but no real activity or any what is it good for. Okay, so this has not been known for any of these compounds so far. Okay, so our intention was to prepare and reproduce this dication which I showed, and actually there was some amount of theoretical investigations done by Professor Jamis and co-workers from Indian Institute of Science, and who found out like these ligands actually quench the charge at the element center, and as you see here, they are not dipositive. Even though you create a +2 charge, significant of the amount of the positive charge is actually transferred to the ligand, and hence they are not so reactive compounds. When we wanted to prepare bismuth compounds, we also saw many of the cations, but the major problem is, number one, they have very high coordination number. Okay, and then this makes them less reactive, and also most of their coordination sites are blocked. So we started with this idea that if you have bismuth in the +3 oxidation state has 3 primary bonds. If you take BiCl3, you see that there are 3 chlorines which go into this. And trans to this, you have 3 Lewis acid sites. And this is the halobismuthates, which Dr. Vijay Kumar was explaining you an hour ago. And so you can actually put 3 halides here and make a halobismuthate. But then you need not have to put a halide or bring in an organic substrate for actually activating your molecule. Then you have a real Lewis acid in hand. So this simple concept was discussed by Norman in an intuitive way in 1990s. Okay, so then what we thought was to actually replace these chlorides, because the chlorides are not that great Lewis acids. They show Lewis acidity, but we wanted to see the limits of it. What is the maximum we can reach? So we actually, in place of the chlorides, we chose a ligand which fits into this geometry. This is called a tris-pyrozolyl borate. It has 3 pyrosol rings bound to a boron. Okay, and as you notice, there are 3 nitrogens which can coordinate, which contribute 6 electrons. Okay, and this is isoelectronic with cyclopentadienyl ligand. Okay, and so the advantage of this is it's a pure sigma donor. It doesn't quench the positive charge generated at the bismuth center. So then we actually wanted to look at various compounds in the periodic table which actually consists of this ligand, and we found that there are not many examples, and here and there people have synthesized these compounds, and they have had terrible times in synthesizing. As you see, there are lots of inclusions of hydrochloride here. Okay, and you have a decomposition of the pyrosol from the ligand, and of course with tin there is only one compound known, antimony nothing is known. So we wanted to see whether we can systematically prepare, and we actually, so I would rather skip some of these things with the want of time, so I go here. So what we did was we took the trichloride and did a salt metathesis, and we got this compound, okay, where we could put the ligand here. Now our next task was to remove the 2 chlorides. If you remove the 2 chlorides, we get whatever I have told a few minutes ago. So you have 3 of the nitrogens binding to the primary bonding orbitals. Okay, I will skip some of these things. Okay, so what we did was we took the silyl cation, which was known by Lambert and co-workers, and we actually abstracted these chlorides, and we got a dicationic bismuth compound here, which is what we rationalized a few slides ago. Now this has 3 acceptor orbital, and this is a unique Lewis acid with multiple Lewis acid sites. Unlike the boron compounds, which has only single Lewis acid site, this has actually 3 Lewis acid sites. So what is it good for? You see here, isolation of this compound was not an easy task. It took around 7 years for us to isolate this. Okay, and you see that the bismuth coordination sphere has been actually stabilized by very weak coordination with the solvent molecules like chlorobenzene and orthodichlorobenzene, and also the counter anion. But these are very weak interactions, and then you can bring in any nucleophile and try to do catalytic activity. Okay. Yeah, so this actually is the molecular orbital diagram which was actually investigated by Jamis and co-workers, and you see that it has 3 of the lowest unoccupied molecular orbitals which show Lewis acidity. These are the 3 lobes which I showed in the earlier slides. Okay, so now we had to show that this is really reactive, and what we chose was reactions with olefin. Okay, reduction of olefins is one of the important reactions in catalysis. People use olefins for reduction of olefins for various things, and you see hydrogen. Addition of hydrogen is one of the most important reactions which is done by Wilkinson's catalyst. Addition of SiH bonds across olefin actually gives new organosilicon compounds. So actually these silicon compounds, you at least find 5 such compounds in everyday life you encounter within 24 hours. This is what many people tell. And then you can, this is one of the attractive reactions, but only successful with heavy metal expensive catalysts involving platinum, rhodium, osmium. Okay, so we have been able to do this with bismuth, it's a p block element, and we have shown that actually this can now reduce this olefins and make new silicon compound using many of these substrates. Okay, and this has been quite successful, and we have not seen any side reactions, which is always the case in many of the transition metal catalysis, and more so that you have a environmentally friendly element to do this type of a catalysis. Okay, so we also wanted to see what the mechanism looks like, and we came to know that this is actually through an SiH activation pathway, where you actually activate the SiH bond and transfer the silicon and the hydrogen moiety onto the olefinic bond. Okay, and we actually wanted to look into a second type of dication. I told you, I discussed one more dication few slides ago, similar to this, okay, where we had 3 tetrahydrofuran molecules saturating this coordination sphere. I told you about the 12 electron compound. So we wanted to first arrive at it. Okay, so we started with a dichloride. I don't want to get into the details of the synthesis because that is not what is important for us at this point of time. But the most important thing is, if you now kick off these chlorides here, which is shown here, if you kick them off, then you end up getting a dicationic species. And this is what we did. We took the dichloride and now treat it with a silver salt. And we do this in presence of a substrate, which is an aldehyde. So aldehyde has a C double bond O. Now you can actually activate this bond. Okay, so the aldehyde oxygen comes and binds to the bismuth center. So this is just a prior process to any catalysis to happen. Now you have an activated carbonyl group. You can start adding anything to that. Okay, and this is what we actually tried to do. So we took the aldehyde, activated it, and added the SiH bond across the C double bond O. And this has been shown for various types of substrates for aldehydes and ketones. And now you can successfully do this hydrosilylation, addition of SiH bonds across ketone. This shows some of the best numbers in main group chemistry. And as you see, it can be done at room temperature in short span of time with high efficiency. Okay. And we have also probed, see, once you generate a catalyst, you also need to know how it works, whether that is the real catalyst, because many of the organic chemists are using many of the salts for doing these reactions, and without knowing, many a times not aware of what the actual catalyst is. We try to screen all the precursors to make sure it is the dication which actually does the catalysis, and we could confirm it was the actually this dicationic species which I discussed in the last slide, which actually does the transformation. And it is, we eliminated the possibility of all the other precursors doing the catalysis. We also try to do some kinetics. So once you have a catalyst, you try to get the rate law, and we found that this is only dependent on the silane concentration, because your ketone comes and binds to the bismuth center, and it is the activation of SiH at the ketone center is what drives the reaction. Okay, so at this point of time, let me conclude at the 50th minute by acknowledging my group. You see here, these are my group members. This was taken a few months ago. We have a very nice waterfalls next to our lab. Okay, and I thank all my group members for their hard work, hard efforts to get high quality results in our lab. And I also thank my collaborators, Professor Jamis from Indian Institute of Science, Laurent Maron from France, and Dr. Babu Varghese from IIT Madras, and all the alumni from our group, and of course the funding agencies, IISER, for providing the state-of-art facilities. And thank you. I again thank all the organizing committee members for providing me a platform to make the presentation. And then thank you all for the kind attention.
Thank you, Dr. Ajay, for that wonderful presentation. Actually, it was very detailed, and very rarely we get to hear about this descriptive talk about Lewis acid. So thank you very much. And anyone has any questions? Let me see. I think there is no questions in the chat box, but you may get some questions in the email.
Oh, okay,
so
okay.
Please reply to them if you get any questions.
Sure,
and
sure.
I take this opportunity, as we are a little late, 15 minutes late as per the schedule. So let me conclude this session by thanking all the speakers. And it was a really wonderful session. Sunoj, Vijay, and Ajay gave very clear lectures on 3 different topics. Actually, it is very different topics, but the talks were very clear. And I take this opportunity to thank Sunoj, Vijay, and Ajay. And thanks a lot for being with FCBS all these years. And I also thank the participants. I know that this is late, and 4 to 7 in probably maybe very busy time for most of you, but you are staying with us, and I hope this will help you in your studies and in your profession. And thank you. Over to you, Raji.
Yeah. So we have come to the conclusion of the second day, and as Joshi thanks, we had a wonderful lectures from 3 different areas, starting from organic chemistry, material chemistry, and wonderful lecture by Ajay on inorganic chemistry. And once again, on behalf of the organizers from IISER as well as from NIIST, I also thank all the speakers, and also I thank Dr. Joshi, one of the organizers, for chairing the session. And though we are a few minutes late, everything was perfect. And once again, thanks to Joshi and all the speakers. So tomorrow, Joshi, we will be meeting at the same time. And
Yes.
Participants. Joshi, yes. Any announcement?
We will have 3 talks tomorrow also. And we will, as today, please log in by 3:45, and then we will start exactly at 4 o'clock tomorrow. And have a good night.
Okay. Thank you. Bye-bye. Chemistry, and wonderful lecture by Ajay on inorganic chemistry. And once again, on behalf of the organizers from IISER as well as from NIIST, I also thank all the speakers. And also I thank Dr. Joshi, one of the organizers, for chairing the session. And though we are a few minutes late, everything was perfect. And once again, thanks to Joshi and all the speakers.